Hi everyone, welcome to this tutorial on Introduction to MDAnalysis and Molecular Nodes. So I'm Fiona, I'm one of the core devs for MDAnalysis. I'm currently a postdoc at UCSF. I'm going to be leading us through the first part of the Introduction to MDAnalysis. But first, we're just going to go through some housekeeping notes. So first of all, MDAnalysis has a code of conduct. There's a link here if you want to read the full thing, but essentially the code of conduct is we want people to be friendly and respectful of each other. Be nice in how you interact with each other and the instructors, and we hope everyone can have a good time here at this workshop. So as Lily mentioned, this workshop is being recorded. So you can also if you want if you want captions while we're going through this workshop, you can also turn these on. There should be the options somewhere in the Zoom settings, as kind of shown here. Then as for how you can kind of interact with us during the workshop, so again, I can see people are using the chat already, so you can use that to chat with each other. If you want to ask a specific question, there's the Q&A option in the Zoom menu. You can also, there's an option to ask a question anonymously using the Q&A if that's how you would rather ask a question. And then if you would really rather try and ask your question directly, you can use the raise hand option in reactions and ask to be unmuted. And you could ask a question that way. Okay. So hopefully most of you have already set up your environment so that you can follow along with the workshop materials. Here's the link again. So if you'd like to kind of start doing that now, though it may take some time to get everything fully set up. But then for those of you who may have downloaded this material earlier, there's been some more recent changes, so slight changes to some of the material, but it's a good idea to pull the repo again just to make sure you've got everything up to date. If you don't have this sort of all set up on your own computer, there is the option to follow along the worksheets from the links on the GitHub page in Colab. Okay, so here's an overview of the schedule. So there's sort of three main parts, where there's two parts introducing to MDAnalysis, and then about going through molecular nodes and the Blender plugin there. So there will be a short break between each of these sections, which will also be an opportunity for more questions if needed. But again, feel free to ask questions throughout each part, and we'll try our best to answer those. Okay, so with that being said, I'm going to get started on the first part. So I'll just move over here. Okay. So yeah. Yeah. Okay, so each part of this workshop So, well, I'm going to start with a shorter lecture component that sort of introduces the some of the concepts here, and there'll be some demonstrations in this. And then there's an interactive tutorial part that you can either go through at your own pace, or I'll be going through that if you want to follow along there. So, yeah. Okay, so let's get started on our introduction to MDAnalysis. So this, in this first part, we're going to go over the basics of how the objects in MDAnalysis are structured, how you can load a system into MDAnalysis, and then if you're using a notebook like we are in this workshop, how you can then visualize this, and how you can use our selection language to select groups of analysis, groups of atoms from your system that you can then go on to perform analysis on. So the general structure of MDAnalysis. So the most important classes here are what we call the universe and the atom group. So the universe essentially contains all the information about a particular molecular system. So this includes the static information, that's things like what atoms are in our system, and the details of all of these atoms. So what name they have, charge, mass, so on, and how they're connected. And then we have the dynamic information. This is the coordinates and how these change over time if we're looking at a molecular dynamics trajectory. So we can then access the information in a universe using atom groups. So we can use these to be able to see the information about all of the atoms or selected atoms within our system. You can also do the same thing, but on a residue level. So if you're looking at a protein, you're able to interact with, rather than individual atoms in the system, you can look at this on a residue basis. And then even one step above that, we've also got segments, which might be something like different chains in a protein system that's got multiple chains. So the very basic workflow for when you're performing an analysis in MDAnalysis would be, first of all, to import MDAnalysis. You then create a universe so that you've got all the information of your system in this universe. You can then define an atom group to specify which parts you're interested in, and then you can collect the positional information of these atoms and perform an analysis. And I'll also briefly introduce at the end, MDAnalysis has a number of built-in analysis that you can run that will do this collecting the positional data and analysis for you, so you don't need to go through the process of gathering the position data yourself. That will also introduce how you can do that. So as for creating a universe, the basic way to do this is using the universe command. And what we need to create a universe is a topology file this contains all the atom information. So like I mentioned earlier, things like the atom names, and then connectivity information. So exactly what kind of information about the atoms will be in there will depend on the particular file type. So MDAnalysis supports a lot of
sorry, Fiona.
Yeah.
If I could just interrupt very quickly, could you please speak a little bit louder? I think a couple of people are having trouble hearing you.
Oh, yeah. Sorry, apologies for that. Here we go. Let me move my. Okay. Is this better for everyone? I don't know if that made any difference.
Yeah, it's better. Thanks.
Okay. Yeah, no worries. Sorry about that. Okay. Okay, so MDAnalysis supports a lot of different file import types. So we can see a list here. And yeah, as we can see, if we look at the types of supported topology files, that these have different attributes based on what the file type is. Then we also have a trajectory file. So this is the file that then has all the positional information about atoms with time. So this could either be, again, a trajectory with multiple frames from an MD simulation, but it could also be just a single static frame. And now some files can double as both the topology and the trajectory. So this is why the trajectory file is optional. So for example, if you load a PDB file that has both the atom names and also coordinates in it. So in that case, you can load a universe with just a topology. So just to give a brief demonstration of that. So we have in this MDAnalysis tests data files, we have some example files. So we're going to load a universe with some of those. So if I just run this box, there we go. So you can see I've loaded a universe here. Okay, so yeah. So then the key properties of a universe. So yeah. So again, yeah, in a universe, so the most immediate thing is that we can get access to all the atoms of the universe using this u.atoms. So this has given us an atom group that contains all of the atoms in our particular system. And again, we can similarly use residues to get a residue group with, say, all the residues in our particular system, or similarly segment. In this case, we just have one segment in our system. Then we can also get information about sort of the bonds, so that the connectivity in our system. And this is kind of, so we'll be talking more about what we can do with each of these later in this session. Then for the positional data, we also have this trajectory for accessing the time-dependent information, and that'll be covered later. So so an atom group is essentially an array of atoms, and we can get information about each of the atoms in an atom group using various attributes of the atom group. So as I mentioned, this includes things like the names. So run this. So this gives us the names of each of the atoms in this atom group. We can also use res names. So this will give us then the residue name that each of these atoms is part of. So we can see, our particular protein that we've loaded here starts with a methionine, and so on. So there's, again, exactly which kind of attributes you can access will depend on what topology file you use to load your universe. And again, you can sort of come look at the documentation to see, based on what particular file you use, what information will be in that. So the way I just showed you there with using u.atoms gives us an atom group that has every atom in the system, but quite often we're only going to be wanting to look at a certain group of atoms. So we use atom selections for this, but first of all, just to kind of help us be able to play around with atom selections, one of the useful things about using a notebook like this rather than just sort of keeping everything in the terminal is we can use this NGL view to be able to visualize our system and our selections. So this will hopefully will be set up as part of the workshop environment. So we can import this NGL view and pass our universe into that, and then we can launch the viewer, and then here we'll see that we've now got this neat little window here where I can see my structure here, and I can sort of play this trajectory if I want and move it around and sort of see the information of different parts of it there. Now, so one of the ways we can create an atom group is simply by directly indexing the full list of atoms. So here we would be saying we want an atom group that's just the first 20 atoms in our system. So you can see we've just made an atom, a group that's containing just those atoms. We can then pass this to NGL view, and we can see here that now it's showing me just those first 20 atoms. But what's going to be more useful is that we want to use selection strings to be able to select certain atoms based on various things. So we have this select atoms command that you can use to be able to select different parts of your system. So this includes things like we have presets like protein, so that'll select just the protein part in your system. You can also do things like so based on the various attributes in the system. So you could say I want everything that's only the methionines in my system, and we can see that we've made a group that's just those methionines. There's also various options for using wildcards, for using Boolean operators to combine different selection criteria, using geometric conditions to make selections, and so on. So you can see these in the user guide, but we will also be going through these in more detail during the tutorial component just after this. So if you do want to, so once we want to get coordinates from our system, we can, from our atom group, use this positions that'll give us an array with all the position data of atoms in that group. So at the moment, this will just be the positions in one particular frame, but we'll talk more about trajectories later section.
Sorry, Fiona, just to interrupt again. Could you please speak a bit more loudly again?
Oh,
Just
okay.
the volume.
Sorry.
Thank you.
Okay. Well, okay, yeah. As I kind of briefly mentioned earlier, MDAnalysis also has a number of built-in analyses. So you can kind of see our documentation and kind of see the various analyses we have there. So again, to run these, you don't need to be able to look into the sort of the trajectory yourself. You can well, how exactly you run each of these will depend on the analysis that you're using. So you'll have to check the documentation for that particular analysis. But usually you'll set it up by sort of passing it a particular select atom group from your universe, and then calling this run method, and then you'll will then be able to access various results from that analysis. So this little quick example here is just setting up an RMSD analysis using the built-in RMSD tool. And then we can do something like plot this in matplotlib. Oops, so that's just a warning, but yes, we can see we've made kind of an RMSD plot over time based on this system. Okay, so so a quick summary of what I just talked about. So a universe contains all the information about our simulation system, and from that universe we can create atom groups which contain the information about just a group of atoms within that system. We can use universe.select atoms to create an atom group based on particular criteria. And then once we've got the atom group set up, we can then access its positions. So I'm now going to move on to the first tutorial. So this is the part where it'll become a bit more interactive if you want to follow along. So either if you've got it set up on your locally on your own computer, you can open it as a Jupyter notebook. You can also, if you would prefer, you can also use the Colab links that are on the GitHub repository to open it in Colab. So that'll give you something that looks like this. To be able to get this to work, you'll need to run these first three cells here. If you're working on your own computer, you don't need to run these. But for working in Colab, you'll need to run these, and it may take a little while. So if you haven't already started that, good idea to do that quickly. And yeah, you'll hopefully, if it works, you'll see a bunch of output that looks something like this. Okay. Okay, so yeah, so now to get started on this, on this first tutorial component. So essentially what we're going to do here is just play around with creating universes, working with atom groups and select atoms, and then also looking at what we can do with the bonds and angle of information that I had also briefly mentioned in the lecture. So again, if you have any questions, feel free to ask them here or outside this workshop. You can also ask questions on, we have a GitHub discussion forum or on the Discord. And you can also check out our user guide and documentation. Okay. So, yeah. So again, the first thing we're always going to need to do is to import MDAnalysis. And then once we've done that, we can then create our universe. So again, for this workshop, we're using some of the example files that we have in our MDAnalysis system. So in this case, our particular example has a PSF file as the topology file and a DCD file that has the coordinates in it. So we're now going to load this universe using MDAUniverse. So you may see this particular warning pop up. So this is just telling us about it. Yeah, sort of upcoming how timestamp stuff will work. So that this is kind of not nothing to worry about. It'll go away if we just run that again. Once we have the universe, once we've created our universe, we can then start creating an atom group. So again, as kind of I've mentioned, we can use this u.atoms that just gives us an atom group that contains all the atoms in the system, and we can then access various information such as so this is the indices of each atom in the system. So from 0 to, in this case, we have over 3,000 atoms in our system. Again, the names of each atom in our system, what the residue name that each of those atoms belongs to. Resids is the residue ID. So so in this case, our particular protein starts at residue 1 and goes to residue 214. So this gives us the corresponding residue ID for each atom in this atom group. Then also, what's the charge of each individual atom, the mass of each atom, and then the atom types. So each of these, you may have noticed, are returned as NumPy arrays. So this means you can do things like index, index into them, so each of these NumPy arrays will be of the same length as the atom group itself, since we'll have one piece of information for each atom in the atom group. So in this case, we're just comparing the if I see how long this, having got the names from my atom group, we can see that we've got the full 3,300 atoms in our system. You can also get the if you want to quickly find out how many atoms you have in an atom group, you can use this NAtoms to see that. Okay. So as well as having a full atom group with multiple atoms. If you, for example, let's take only so I'm using indexing here to access only the first atom in my system. And rather than a whole atom group, this is going to give me just a single atom object. And like with atom groups, I can access things like what's the name of this atom, what's the residue name that it's part of, or the residue ID that it's part of. And rather than then giving these as arrays, we'll get these as just single values. Usually, this is discouraged to work with individual atoms, so you're probably going to, it's going to be more useful to stick with atom groups. So I also mentioned in the lecture component that we have these residues and segment groups. So we can also create a residue group with all the residues in our system, or a segment group with all the segments. So this is for if you're wanting to work with things in your system on a residue or a segment basis. And similarly, you can do things like find, well, what's the residue name of each of the residues in my system, or the ID of each segment in my system. You can also convert between these. So if we started with an atom group and we now want to turn this into a residue group, we can use this, so we're taking our atom group and using dot residues to then get a residue group that way. Okay, so we now have some exercises here. So I'm going to be quiet for a little bit and give you a couple of minutes to have a go at some of these exercises. There are some solutions here if you want to peek ahead, so I'll hopefully give people maybe 2 or 3 minutes to have a go at that, and then I'll be back and I can go through some of the solutions there. Again, if hopefully everything has been making sense so far, but feel free to ask questions if you have anything you want to ask.
While people are working as well, if people want to turn on you don't have to, but if you'd like to turn on your videos as well, so we can feel less alone while we're presenting to you all. And yeah, feel free to raise your hand and ask questions in the chat, which people have been doing.
Okay, so hopefully people had a chance to at least try and play around with some things themselves there. But then just to go through these exercises. So, so I'm just going to show the solution here. So this first exercise was just getting us to, so first of all, we wanted to get this example grow topology file from our example data file set. So we can do that like we saw in the earlier examples, where we can import this from the MDAnalysis data files. We're then loading a universe. So in this case, because grow file contains both the topology information, so the atom information, and coordinates, we can load a universe by using MDAnalysis.universe with just the grow file. So we don't need a second file there. Oops, sorry, I've got a cat in my ear. Okay. And then it wanted us to say how many atoms, residues, and segments were in that file. So there's several ways that you could do this, but in this example solution, we're doing this by creating the atom group with all atoms in our system by calling atoms, and then we can use this n atoms, n residues, and n segments to count the number in each of those. Now moving on to the second exercise, this is now asking us, using this universe, let's select particular segments, atoms, or residues from this. So again, to just show the solution here. So so in order to find the name of the first segment, first of all, we're creating the segment group of all segments in our system. We can then index that. So because this is 0 indexed, the first one we can find it will be 0 here, and then getting the seg ID from that. Similarly, then if we want to find the name of the last atom, we use atoms to get the atom group of all atoms. Minus indexing to -1 will give us the last atom, and we can then find the atom name using .name. And then finally, if we wanted to find the 10th residue, we get the residue group of all residues. Again, since this is 0 index, the 10th residue we use by indexing a 9 here, and then find the res name of that. Okay, so hopefully people have been following so far. Hopefully, sorry, my cat is not getting in the way. Okay. So again, yep. So we're now going to go through a bit more on how we can create atom groups based on particular selections. So since an atom group behaves like an array itself, so we can index directly into this atom group. So like we were doing above to select just, say just the last atom here, we can also feed in a list of numbers in order to select an atom group based on each of these indices. So here I'm feeding in 4 numbers to create an atom group of these 4 particular atoms. You can also feed in a range to be able to, so in this case we'd be getting the 9 atoms from our system from index 1 to 9. Some of the other things you can do is using Boolean indexing. So what this means is that I can use this. So if I get all the res name properties of all the atoms in our system, and then I want to check if these are glycine or not, this will give me a list of true false values that as we can see here, that I can then use to feed this back to my atom group as a way to create a selection from this atom group that will only have the atoms where the residue name is glycine. You can also do this in sort of one line by including this comparison directly in the brackets. And similarly, you can do index into residues and segments in a similar way. However, it's going to be a lot easier to use in most cases, to use the selection language. So we have this select atoms method. So you can see kind of the information from the doc string here if you run this cell. And there's also more information in the docs if you kind of want to follow that link. So yeah, this is where in the example above, I showed you a way that we could get just the atoms that were in glycine residues. We can also do this using our select atoms by asking for, so in this case would be asking for atoms where the res name is glycine. So we can see we've created an atom group with the same 141 atoms as above. We can also use this to select, say, a range of residues. So I'm specifying here, I want all the residues between residue 1 and 10. And we can see we've created an atom group there. And then we can, if we want to start building these up, we can use logical conjunctions to do things like, so if I wanted to select both more than one residue based on their name, we could use an OR to link these. So in this case, we're selecting all the acidic residues in our systems by asking for both, if the residue name is either glutamate or aspartate. Then we can use wildcards. So this comes in useful for, so if you're looking at, say, again, a protein system where, the atom names, you might have something like OD1, OD2, etc. And if you just wanted to select, select all of these atoms, you can use wildcards so that this will match any atom that has a name that begins with OD. And then again, you can kind of start grouping together any different kind of selection as you want, using and or and kind of using brackets to separate these out. So you can see in this case, we're making a selection where we want specifically atoms with one of these two names, but only if they're also in a lysine or an arginine residue. And yep, again, there's some pre-built-in selections. So if you wanted to only look at the backbone of a protein system, you could do this manually by asking for only the atoms that had a name that was in, so the alpha carbon or CON from the backbone, or you can use the built-in selection that's just backbone. And this cell is just showing that these two selections give us the same thing. Now, something that's also useful is there's also geometric selections. So this will allow us to select atoms based on their position relative to other ones. So say, for example, if I'm trying to find salt bridges in a particular system, I could look for, in this case, I'm asking it to show me, so this is also using some built-ins, but asking it to show me or give me an atom group that has kind of acidic, or atoms from acidic residues that are around 4 angstroms to a basic residue. For all of these, you can check the documentation for exactly what the format for using these various geometric selections are. So in this case, for selecting within a particular cutoff, we use this around. We then specify what the distance cutoff we want is in angstroms, and then the selection that we're using to say this is what I want my selection output to be within 4 angstroms of. You can also do things like, so for example, if you only wanted to find atoms that were had a z coordinate above a certain value, you can use this prop property, in this case, z greater than 10. And this will just give us all the atoms that have a z coordinate above, again, above 10 angstroms. There's also, again, so more things that you can do. So if you have multiple atom groups, you can then combine these. So for example, if I've got one atom selection where I'm looking at, so I'm trying to find all the atoms that have a mass above 10, and then I've got a second selection where I'm just finding all the atoms that are arginines. We could then combine these using just an AND operator. So you can see my initial atom groups had 1,600 and 300 atoms respectively. And then if we use this AND operator to combine them, it's found only the atoms that belong to both groups. So we've only got 140 atoms there. So this means that something like, yeah, that these two ways of making atom groups that have making an atom group that has all the lysine and arginine residues in it, we can either do that in one go by just having the, selecting res name lysine or arginine, or we could create two separate atom groups, one where we select all the lysines, one where we select all the arginines, and use this pipe here to combine these to create an atom group, a group of atoms that belong to either this first group or this second group. So we can see here that these two give us the same thing. So this could be useful in several cases. You can also build up atom groups by essentially just adding them together, or by subtracting them. So again, a lot of these things you can do in multiple ways. So you can create a selection using an not in front of or within the selection string. So in this case, we want to find atoms that are in a lysine or an arginine residue but aren't a hydrogen atom, and we can do this in just one selection string like this, or we can also, if we've got separate atom groups, one that's the lysine and arginine residues, and then one that's all the hydrogens, we can just subtract these, and again this gives us both of these will give us the same atom group. So there can be various reasons that either of these might be preferred in a certain situation, but it's useful to know that both of these options exist. You can also repeat indices in when you're creating an atom group, so that you can have multiple instances of an atom in one particular atom group. So you can see here, even though some of these indices are the same, we've got an atom group that's got 7 atoms in it. But we can then use this unique to make sure if we only wanted to get unique atoms in a particular atom group. Okay, so we're now at another set of exercises. So again, I'm just going to give everyone a couple of minutes to have a go through this yourself, and then I'll be back after those couple of minutes to take you through the solutions. Again, feel free to ask questions.
Fiona, we got a question in the chat about selections, and the basis of selection being the positions of the atoms. which can change as you go through a trajectory. Did you maybe want to talk very briefly about updating atom groups and what you can do with those?
Yeah, so you can, there is an option, I don't know if it's, yeah, so there is, yeah, so when you're doing selections that are based on positions of atoms, so as our questioner and Lily just mentioned, then if the positions are changing in each frame of your simulation, this means that your these kind of criteria or these properties are going to change. So yeah, you can when creating your atom group, you can use this this little updating flag will make sure then that, for example, if I wanted to make sure that in each frame of my simulation, I'm only selecting the atoms that, based on the coordinates in that frame, have my certain position requirements. This will make sure that it updates every frame. Otherwise, yeah, otherwise it will depend on the sort of the frame that your trajectory was currently on when you create the atom group and look at it. It'll base that on, yeah, sort of what the current frame your trajectory is pointed at. Yeah, hopefully that made sense.
Thank you for the validity tool.
Okay, right. So let's move on to looking through the solutions to this set of exercises. Yeah. So first of all, yeah, we're just wanting to select the residues from 100 to 200 in kind of two different ways. So again, we can use this using directly indexing into the residue group. I'm using, yeah, directly indexing there, or we can use the selection string language to yeah, find all our residue IDs from 100 to 200, and we can see that these are true here. So again, there can be different reasons why one method might be preferred over another. So this could depend on, your residues may not always start at residue 1. So it may be that you know the particular residue number you want to look at, but not exactly what index it will take in the in kind of the list of residues. So that might be a reason to use the selection string. And on the other hand, you might know that you want to look at the first residue in your system, but you don't know what exactly residue ID that has, so you might prefer to use directly indexing in that case. We're then asked to count the number of arginine residues. So in this case, the first thing we can do is create an atom group where we're selecting all the, by using resname, all the arginine residues. And then as for counting how many of these are, again, there's several ways you can do this, but in this case, we can just see what the length of the sort of residues that residue group that we make from this atom selection, and we can see there's 13 arginines in our system. Now for a geometric selection, so we're asking to find all the nitrogen atoms within 5 angstroms of an alpha carbon. So to do this, so we're asking to find all nitrogen atoms. So because So different nitrogen atoms in our system might have different names depending, exactly where they are on the protein, but they should all begin with an N. So we're using a wildcard to select all nitrogen atoms, and then we're saying, but we also want it to be within 5 angstroms of any carbon alpha atom, which should have the name Ca. And you can see we've made an atom group now with just all of those nitrogen atoms. And then lastly, select all hydrogen atoms that are bonded to an alpha carbon. So this is one of the options that I didn't talk about, but to kind of show you another thing that we can do with the selection language is there's also this bonded option. So in this case, we can use this to say we want any hydrogen atom that is also bonded to a carbon alpha atom. So now to play around with NGL view. So again, we can import this NGL view and feed it our universe. So we'll get that set up there, and then we can launch the viewer, and now we can see our system here. So again, this can be useful to make sure to give us a quick look at what our system looks like and make sure we're loading the right thing. And then we can also use it to so sometimes when you're just typing numbers into a script, you don't always know that the numbers you're typing in are selecting exactly the right thing. So this can be a nice sanity check. For example, if I wanted to select the first helix in this protein, and I thought it was residues 12 to 25, but just wanted to make sure, I can make a quick visualization of this and go, oh yes, good, this looks like a helix. This is what I expect. You can also add multiple representations to the same view. So if I wanted to then see, okay, I want to make sure that residue 20 is the residue I think it is, you can add this to the viewer, and I can see my residue 20 here. So I can see that, oh, yep, it's an isoleucine, it's where I expect it to be, and so on. So now let's have another exercise. So so again, I'll give you a couple of minutes to just quickly play around with NGL view, and then there's an exercise for you there. Okay. Okay, so since we're just starting to run towards the end of our time for this first section, might start going through this solution now. So we are asked to show all atoms below a certain plane, x equals 4. So just, all atoms with an x coordinate below 4. So we first make an atom selection. We can use this prop to make an atom group with all atoms with x less than 4. We can then feed this atom group into NGL viewer and then show that. So you can see here, if I rotate this around, that we've made this selection where we've made a neat slice to make sure we only see atoms below a certain plane. So this might be useful in context. For example, if you're looking at a membrane protein system and you want to find all the atoms that are below the membrane, or so on. So now the last part of this this tutorial, we're going to quickly go through bonds, angles, and dihedrals. As mentioned, so this is something that will depend on the topology file that you're inputting, whether this bond information is already present. So if I try, this is, okay. I know why this is doing this. Okay. Oops. Sorry, bear with me here for 1 second. I don't know. Okay. Oops. Oh, okay. Whatever. Okay. So because I already ran this workbook before this to make sure everything was still working, it's already given me the warning, and now it doesn't want to give me the warning again. But hopefully, if you're running this yourself, what you'll see is that when we try to load this this universe, it'll pop up with a warning that it couldn't find bond information for this universe. Oh, actually, I know why it's doing that, because I haven't run the right cell. Do ignore me. Okay, so here we go. Here's the warning I was talking about. Yeah, so you can see here it's complaining that this universe does not contain bond information. So when I try to look at the bonds in our system, it can't find them. But what we can do is we can use this guest bonds information. So this is going to, yeah, based on the positions of all the atoms in the system and sort of how close they are to each other, is going to try and guess what all the bonds, all the atom bonds within the system will be. So that takes a little while longer to run, but now if I do this, I can see I can now use this dot bonds to find a topology group that contains all the bonds in our system. Similarly, I can then find all the sort of sets of angles between connected atoms and dihedral angles between connected angles. And much like atom groups, we can index into these to find a particular bond. So if I tell it to tell me what's this would be the fourth bond in our system, I can see that it's a bond between atom index 0 and atom index 4. We can then access the properties of these bonds. So if I just go to u.atoms.bonds is the full list of bonds, and I ask it to tell me the values of these. So this is giving me the bond length of every one of those guest bonds in our systems. And I can also access the value of just a single bond, and that will return me just the length of that particular bond. So we could do something like, if I wanted to know what's the distribution of bond lengths in my system, we could use this, and then I'm using matplotlib here to show us a histogram plot of that distribution. So again, if you are interested at looking at certain bonds in your system in this way, rather than sort of trying to find them just using atom selections, so we can, for example, yeah, I can see if I look at this, all the bonds in the universe, and ask what their types are, you can see that when it's identified bonds, it's identified them between sort of these particular pairs of atoms. So I could use sort of this select bonds terminology to, in this case, I'm selecting, so if I'm only interested in the bonds between carbon and nitrogen atoms. So kind of one of the things that maybe you can kind of do with this. Yeah, so if we wanted to say, for example, look at the dihedral angles associated with the background of our protein, we can, so for example, I'm looking at this residue 2 here. We've got these built-in options. So these are built-ins that will return us like an atom group that has the atoms involved in the phi, psi, or omega dihedrals. And then I can use this dihedral that will then give me this dihedral property that's between these atoms. You can also kind of manually create a bond between atoms if that's something that you kind of want to set up. Or similarly, if you wanted to create this atom group. So that you can use this if you then want to be able to quickly get, say, the distance between two atoms or the angle between three atoms. So very quickly, if you want to, I'll give you just a minute to try this very last exercise here, and then I'll quickly go through the solution. Okay, so then just to quickly go through this solution so people still have time for a quick break before the next section. So we were asked to calculate the angle between three particular atoms in our system. So what we've done here, so what we're doing is, first of all, we want to create an atom selection with these particular atoms. So the way we've done this here, again, as always, there'll be several ways you can do this, but in this example solution, where first of all, taking kind of the set of all residues, using indexing to take the fifth residue, and then we can directly turn that into an atom group instead of a residue group, and then directly select the atoms from that residue group that has the name Ca, so our carbon alpha. And we're doing that 3 times so that we can get the carbon alpha for the 5th, 6th, and 7th residue. We're then creating an atom group that's combining these 3. So using the selection language, you could do this all in one step, but we're showing this in this particular example just so that you can see some more usage of some of the things that you can do with atom groups and residue groups. Then finally, what we're doing is we're taking that atom group, turning that into an angle group, so that we can then take the value of that angle. So yes, you can see here that we've now got this angle here. So that saves you from having to kind of manually figure out an angle between 3 residues by finding the position of each and doing some trigonometry between those coordinates. Okay, so that brings us to the end of this first part of this workshop. So we're now going to, we've now got a short break. So if people need leave for a moment, take a break, refill your cup of tea or anything like that, you can do that. Or you can ask more questions. And then we'll be back, shortly to start the second part of this workshop.
There's a question in the chat about how we normally use MDAnalysis. Like I said, it varies a lot. Generally, I usually prototype my MDAnalysis work in Jupyter just because you can iterate really quickly. You can see when things are breaking. You can sense check things like looking at your selections in NGL view to make sure that you're actually working with what you want. But then after I write, I'm happy with my code, I do typically put it into a Python script and then run it like that. Especially since I'm normally running on a cluster or something, that's not my local laptop. That being said, I haven't actually used MDAnalysis in work for a couple of years now, so someone like Fiona might have a different answer.
I'm pretty similar in that. So most of the time I'm using MDAnalysis, it's directly in Python scripts. But if I'm I guess writing a particular script for the first time, then yeah, doing it in a notebook can be useful. Again, particularly to make sure that I'm selecting the things that I think I'm selecting. But usually that will kind of just be the initial stage when I'm first getting used to, if I've started doing simulations with a new protein. And kind of once I kind of got that figured out, I'll usually just use Python scripts. But I think, yeah, it's probably very much personal preference, kind of as to how everyone wants to go about it. Okay, so that brings us to 25 past by my clock now. So I might hand over now to Lily is going to take the second part of the workshop here.
Okay. Everyone can see the slides? Cool. So I'm going to start talking a bit more about like the inner workings of MDAnalysis, some of the stuff that's happening under the hood, and some of the more powerful tools that we ship. This format will be quite similar to Fiona's, where we'll start off by, I guess, introducing a lot of the concepts and the functions that we then apply in the tutorial. So like Fiona, I'm working off a lecture notebook. I'm going to run it off my local laptop here, just because I can use my Jupyter extensions and I can format it like slides. That being said, if you would like to follow along and execute these cells, you can open this notebook in Colab, where it will look like this. And if you do that, please just install the required packages that you need for this particular notebook, which in this case is just MDAnalysis and the data files that we'll be using. So these two cells. Alrighty. So yeah, onto the slides. So this part of MDAnalysis is mostly going to focus on distance calculations. So where Fiona kind of introduced the user interface of MDAnalysis, if you're just starting out, how to load files, how to run the inbuilt analysis that we have. The functions that I'll show you today are a bit lower level, and they'll be quite helpful in helping you write your own analyses. So as Fiona introduced, the positions data that we can look at lies in the positions attribute of an atom group. So if I execute the cell, you can't quite see the whole thing, but what I'm doing is importing MDAnalysis. I'm loading in these test data files, a GRO file and a TRR file from GROMACS, and I'm creating a universe. We're using the selection language here again to select the protein, and we're just going to print out the positions of the protein as shown below. And we're also going to print out the length of the atom group. So the protein has 3,341 atoms, as well as the shape of the positions array. So in this case, the positions array is the number of atoms by 3, where the first column is the X, the second column is the Y, and the third column is the Z coordinate. So MDAnalysis has some built-in functions that you can already run on position data. Some of the useful ones are center of mass and center of geometry. You can just apply these to the atom group that you created, and they will give you the respective centers. I should just say that the center of mass, of course, depends on having the right masses in your topology file. So if you have, for example, loaded in a coarse grain PDB where there aren't any masses included, you should really not use this function because what comes out is going to be quite inaccurate. One of the big things that I want to introduce in this particular session is the distances module. So this is one of the more powerful parts of MDAnalysis. And despite sounding a bit boring, just measuring distances between atoms, it's one of the more useful ones. So because the positions are given as NumPy arrays, a lot of the work that we want to do can actually already be done in NumPy. The reason we want to use the distances module is because in our simulations, just measuring the distance between two atoms is not always straightforward. We often simulate in in cells with periodic boundary conditions, where if, for example, your box is this big and your atoms actually break the boundary or cross the boundary, the kind of naive distance that you can calculate with NumPy is actually not the accurate one if you look at it in simulation. So from MDAnalysis, I'm going to import distances. Oh, and I should just say, yeah, please continue to ask questions in the chat or even unmute yourself or raise your hand, I should say, and ask live. So the first function that I'm going to introduce is the distance array. This is maybe the most important function in the distances module. If you only remember one, remember this one. And this will calculate all pairwise distances between two arrays of coordinates. So in this demonstration, for example, if I create two atom groups, one that has 10 atoms and one that has 20 atoms, I can calculate all the distances between every atom in the first one and every atom in the second one. If I want to include periodic boundary conditions in this calculation, I can pass a box size to the distance array function, which in this case just passes the dimensions of the cell. So if I execute this, you can see that we have an atom group with, or two atom groups with 10 and 20 atoms, and our output has a corresponding shape of 10 by 20. So we can actually use that, I think, in the next cell. Oh yeah, exactly, to index the results. If, for example, we want to get the distance between the fourth atom of the first atom group and the sixth atom of the second atom group, we can just use the same indices here to index the results, where dA, as shown above, are the distances that we get at. And keeping in mind that we index from 0, so the 4 turns into a 3. The second function that I want to do is, or show you, is self-distance array. So this is really similar to distance array, but if, for example, you don't want to calculate the distances between two different atom groups, you just want to calculate all the distances between every atom in one group, you can use this one instead. So this takes a single array of coordinates and calculates all the distances between every atom to every other atom. Unlike the distance array function, this doesn't give you like an n by m matrix out. It gives you kind of a triangular matrix where it only calculates, like it doesn't do every calculation twice. It's a triangular number. It makes sense if you kind of draw it out. So if I run this cell using the first atom group that I had before with 10 atoms, we can see that the output has shape 45. And yeah, so you might be wondering, sorry, before I move on to calc bonds, exactly what you can do with this. It can be a bit tricky to, for example, work out what to do if you want, say, the distance between the third atom to the fifth atom. What you can do is you can paste this, paste this into a normal matrix using NumPy functions, or you can just kind of work out which one you want by calculating the index yourself. The next function that I want to show, just going through these a bit quickly, is calc bonds. This is a bit of a misleading function because I guess it's not misleading, it's kind of part of a pattern. We have calc angles and calc dihedrals later on. But what it really does is, instead of calculating bonds, it calculates the distances between, I guess, pairs of coordinates. So what you need to do is you need to take two arrays of coordinates. They have to be the same length. And for each position in the corresponding index, it responds to it returns the distances between those pairs. So for example, again, if I take the coordinates of the first 10 atoms and the coordinates of the second 10 atoms, I can calculate the distances between each of those. And I should clarify that because these are just positions, the atoms don't have to be bonded to each other. They can just be random coordinates. So moving on to calc angles and calc dihedrals. This is very analogous to calc bonds. So again, you can calculate the angles between 3 arrays of atoms, or the dihedrals between 4 arrays of atoms. So this is unfortunately not showing entirely, there we go, on my screen. Hopefully everyone can see that now. What's shown here, firstly, is the calc angles function. Again, it's very similar to the bonds, but you pass in 3 arrays of atoms instead. And again, they have to be of equal length. With dihedrals, if you're not very familiar with dihedrals, they're basically the angle between 2 planes. So if you think about a linear chain of 4 bonded atoms, atom 1, atom 2, atom 3, and atom 4, add that finger there. It's kind of the rotation between these two planes, where the first plane is defined by the first 3 atoms and the second plane is defined by the second 3 atoms. So again, calculahedrals will take these 4 arrays of coordinates and treat them as linearly bonded, kind of, and calculate the angle defined by those planes. So calc bonds, calc angles, calculahedrals, much like the distance functions shown before. We haven't shown it here, but each of these takes a box argument, which allows you to apply periodic boundary conditions to each of these calculations. And that can be really, really helpful because, again, if one of your atoms crosses the periodic boundary condition, just the periodic boundary, it can get really finicky and difficult working out how to exactly calculate that angle. So if someone's already done the work for you, it makes sense, I guess, just to use this function. So, okay. I got a bit ahead of myself. It turns out we actually have a section on this in the slides. To account for periodic boundary conditions, as I have mentioned before, you can pass the box argument to any of the functions that I've shown in this module. So what this means is a bit more quantifiably, it makes the measured distances equal to the minimum possible between all periodic images of those coordinates. So, for example, we have been working with a universe that has dimensions. In this case, it's a fairly equally sized box. The way to interpret this is the x-axis, y, and z-axis. They're all 80 angstroms long. And these last 3 are the angles between those primary axes. So because these 2 first angles are 60, this is actually a triclinic box. It's not one of the cubic boxes. It's kind of like squished or slanted. So again, if we select a protein as an atom group, what we can see first here is that the maximum distance between each atom in the protein to any other atom in the protein is 89 angstroms. So clearly, because that's larger than one of the axes of the box, this is actually crossing periodic boundary conditions. If, however, we want to include box information, we can run the cell again. And we can see that when we take these boundaries into account, the maximum distance is actually only 51. So I typically almost always include periodic boundary conditions when I do distance calculations, but you do have to, I guess, ask yourself if that's always appropriate. For example, you might be trying to measure something in a protein that does cross the boundary. So yeah, have a think about, I guess, every time you run a distance calculation, whether or not you should be considering periodic boundaries or not. So moving on to cap distance and self-cap distance, these are very similar functions to what I've shown before. So where before I've shown already distance array, self-distance array, and some of the smaller functions, calculating bonds, angles, and dihedrals, cap distance kind of goes back to the same big functionality as distance array and self-distance. The difference here is that it only finds distances up to a maximum limit. So even though I guess all the calculations that I've shown currently have been quite fast, they do scale quite terribly as you increase the number of atoms involved. So in that case, if you know that you only care about distances within a certain limit, this can be much more efficient when dealing with large calculations. So if we wanted to apply this to a real example, for example, a hydrogen bond analysis might look like this, where you select your hydrogen atoms. So in this universe, our water is called Sol. We're selecting all molecules with the residue name Sol, and we're selecting all the hydrogens by type H. With acceptor, the acceptor atom group, we're selecting all our protein atoms, but within those protein atoms, we're selecting all the nitrogen and oxygen types within the protein. And this is a bit of shorthand, so this is type NO. This is a bit of a shorthand for protein and type N and type O. It gets a bit tiring, I guess, typing out too many of those. So we can also shorten it into just a list of types. So if we run this, we see that in our universe, we have 22,000 hydrogens in our waters, and we have 609 possible acceptors. If we want to calculate the distances between those two atom groups, we can use cat distance to calculate, again, just the positions between those atom groups. We can set a minimum cutoff. This is a bit of an optional argument, but it tells us that we only care about distances that are higher than 1 angstrom, a maximum cutoff, and again, we can pass in these periodic boundary conditions. So if we run this, we get out two results. The first is an array of indices, and the second is an array of distances. So I guess, yeah, we print out a subset of those here. So the array of indices is a column of the number of distances that fulfill that constraint. So for example, if I actually print out the length of the indices, that says that we have 2,602 cases where there are hydrogens between 1 and 4 angstroms of acceptors. And if we wanted to actually look at the distances involved, we can look into the distance array. In this first column, we get the indices of the first atom group that we pass in. So this is the hydrogens atom group. So this is saying that the second hydrogen in this atom group with index 1 is within is around between 1 and 4 angstroms of the 134th atom of the acceptor atom group with, again, index 133. So I made claims earlier that cat distance is much more efficient than just using distance array and searching for your own distances. If we run this in a Jupyter notebook, it has this magic timer that can let us time how long functions take. So we can actually demonstrate this. If I run distance array on the calculation I just did, that takes about 388 milliseconds. Whereas if I run cat distance with the constraints that I set, that's about 30 milliseconds. So yeah, as this slide says, it's about 10 times faster. So over this lecture, I've covered a few different distance functions that we can use in MDAnalysis. Calc bonds, distance array, self-distance array for calculating distances. If you want more efficient distances, we can use the cat distance functions. And if you want angle functions, you can use calc angles and calc dihedrals. And I guess we'll have a look at how to apply these in the tutorial section that also comes with the session. So again, if you have a look at the notebooks in the GitHub repo, you can run this tutorial in your local environment, which I probably will. Or again, you can navigate to the Colab and follow along with the Colab functionality instead. So yeah, are there any questions so far before I get into the tutorial?
Yeah, there was a question in the chat about when you wouldn't want to consider PBCs.
That's a good question. I basically always do. I guess in some cases, for example, if you've post-processed your trajectory already, for example, in GROMACS, if you've unwrapped your trajectory, it will still have the box information. So you don't want to consider that again. If you, for example, have changed the coordinates. Otherwise, yeah, I can't think of many other applications in my own personal use.
So theoretically, well, sorry to interrupt, but I guess, yeah, similarly, also everything I do, I'd probably be wanting to consider the periodic boundary conditions, but it could be that you might have, you know, a file or a system that, you know, just isn't something that you had run with periodic boundary conditions in the first place, so it just wouldn't make sense to do that in MDAnalysis. Like if you were, you know, running a system that was just literally one static box. So it's the kind of thing that it may not be useful to everyone, but it's good to have the option there.
Yeah. Yeah. In that case, sometimes you can also load in trajectories where the box information is actually just none. Although you can actually just pass that to the function as well, because the default argument to the function is also none.
Yes.
Yeah. Alrighty. In that case, I might move on to the tutorial. I've loaded it locally because we have all these nice things locally, like a table of contents and those exercise cells that Fiona showed earlier. But yeah, let's get into it. So again, we start off with imports. What is this warning? This is not an important warning. This is just something that we should deal with in the base package itself. And we fetch our data set. This might take a few minutes for this and for the 80K example below. This is just using a larger data set in MDAnalysis data for demonstration purposes. I've preloaded it, so it's fairly instant for me. We create a universe and we load our first residue. So this universe is a bunch of polyethylene glycol chains of water, I think. We can actually have a look at it. So I think this cell only shows the first residue, but we can also have a look at the whole thing. Oh, maybe not. Okay, it is just the one cell, one residue. And we can also, I guess, watch it wheel about in simulation. So again, as shown in the lecture, we can look at the positions as an attribute of atom groups. So we create an atom group of all the oxygens in the universe, as shown by type OS. And we can look at the positions just here as an array. As shown in the lecture, we have a few different functions that can be applied to the atom group. So I've already shown center of geometry. Although in this case, we can actually show alternative ways to do it outside MDAnalysis. So for example, the naive way to do a center of geometry would just be to average all these positions, which we can do with NumPy. So if I do that, if we average over the first axis, we get the center of geometry according to NumPy. If we do it with MDAnalysis, we get the same result. So there are quite a few of these functions that you can use on these atom groups. Another one of those is the radius of gyration function. So one of these exercises that we can do is actually to also calculate the radius of gyration of PEG. So this is, I guess, an exercise. So I might give it a few seconds or a couple of minutes if you want to do this yourself before I keep going on with the tutorial. Okay, this is a pretty short one, so I might start moving on. What would you do? You would, I guess, take your atom group that you had before earlier. So PEG, poly, no, just PEG. And you can just apply the radius of gyration. And I think in Jupyter, if you hit tab, you might be able to get this to show up. No. There is sometimes a helpful pop-up that can show up all the properties that you can apply to an object in Python, but it's not working here. Oh, that's not working. It is a method of residue group. Okay, so PEG, because PEG is a residue, I have to actually look at the residue group of it, which you can access with residues. And it does not have an attribute residue. Okay. So I can do this two ways. I can either do PEG u.residues, that should be a residue group. Although before I put my foot in my mouth again, I would just try this. There we go. Or using the sum method, I can go PEG and I think apply it like this as well. Oh, cool. Okay. How many residues are there in this universe? Okay, so that makes a lot more sense. There's 4,422 residues in the universe, and the radius of gyration of all of them is 161.2 angstroms, whereas the radius of gyration of one of them is 10.5 angstroms. And what I did here is the sum function is a built-in function in Python, but when you apply it to atoms, residues, and segments in MDAnalysis, they actually give you the group corresponding to that particular level. So for example, if I did some peg u.atoms, the first atom, that would give me an atom group with only one atom, that being the first one. And you can look at the type here if you just hit enter. Okay, so moving on a bit. The next section is talking about bonds and distances. So the first thing that we're going to look at is the end-to-end distance of a peg chain. And we can do that by looking at the hydrogens in the capping hydroxyl groups or using those as reference points. So if we select those here, we're going to do this using pre-existing knowledge that they're called HO. This is obviously going to vary depending on the universe and the data files that you're working with. So you're going to actually have to know what your atoms are called before you start doing this kind of thing. But in this case, we're cheating. We know that they're called HO. And here again, normally the select atoms function would return you an atom group. So for example, if I just run this cell, that's an atom group with 2 atoms. What I'm doing here is I'm not actually sure what this is called, but I'm using a Python functionality that lets you assign this to different variables. So I'm just assigning the first atom in this atom group to HB and the second one to HE. So if you run this cell instead, HB is an atom, as is HE. And what are we doing? We're getting the distance between these 2 hydrogen groups. So again, we're going to show you the hard way of doing this first, or the normal way of using NumPy, where we create a vector between the 2 hydrogen groups by taking the difference between their positions. And then we just take the distance as the magnitude of that vector, which you can do with the norm function. And so from there, we get a distance of 25 angstroms between the 2 hydrogens. That being said, as shown in the lecture, we actually have a function that can do this for you called calc_bonds. So the equivalent function in MDAnalysis would just be doing this, using the position of the 2 hydrogens and calculating the distance with periodic boundary conditions, which in this case is still 25.3 angstroms. We can also apply this to calculating angles as well. So this is actually going to be a different data set. And I'll talk through the problem below, but maybe run this cell first if you haven't already, because I think this can take like 5 minutes to actually download the data. So again, I'm using MDAnalysis data to fetch a larger data set, and I'm creating a universe from that data set. So this data set includes a protein that Fiona used in her session as well, a denylate kinase. This is a slightly different trajectory, as this one actually shows a conformational transition. So this trajectory transitions from the closed state to the open state with a corresponding change in domains of the protein. And what is common in these conformational state changes is to want to be able to visualize that and quantify that. So one way that we can do it is by calculating the angles between these domains, where these domains, the lid, the core, and the NMP domains are, I think, fairly standard in ADK. So again, if we look at the ADK protein, we can define those domains as these particular residues, with the core domain being this set, NMP being this set, and lid being this set. And we can use these domains to calculate the angles between them to distinguish the open and the closed states. And we can define these particular angles as between the center of geometry of the backbone and the beta carbon atoms of these particular groups, which we've written out for you just for the sake of this problem. So if we know all this, we can then calculate the angle between vectors. And this is the standard way to calculate, I guess, the angles between vectors, just kind of written out. And we're going to step through that first manually using NumPy to show, I guess, how painful it is, and then do it very fast with the MDAnalysis way as well. So firstly, to do this, we need to define the coordinate centers of each domain. So for example, for N and P, we can select all these particular groups and get the centers of geometry for the atom groups, which I'm just going to execute and do. And again, if you look at these, they're just arrays of a position. With these positions, we can then define vectors. So from B to A is this vector, and from B to C, or from C to B, no, B to C is this vector. Once you have the vectors, you can calculate the angle between those just using the formula shown before. So this is just the NumPy version executing the formula shown before, this arccos, and that gets you theta. Theta will be in radians. So when we print it out, we also want to convert the radians to degrees. And then we can repeat that entire process with this angle as well. And ta-da, that gets you the angle between for these two sections. So 43.7 angstroms and 106.4. Of course, the MDAnalysis way, using calc angles, is much faster. You basically just pass it those same centers of geometry that you defined earlier, and it will calculate the angles for you. Ta-da, we get the same result. That being said, though, it's sometimes good to actually just step through this kind of thing and work through it with NumPy. This is basically what it's doing under the hood, just much more efficiently and much faster. And much like NumPy, the output is actually still in radians. So I guess make sure you're converting it to degrees if you're expecting the angles to be in degrees. And as covered in the lecture, we can also specify periodic boundary conditions using the box argument, if that will matter to us. Alrighty, any questions so far on the bonds and the angles section? If not, we're going to kind of take a lot of what we've done before with these distances and angles, and we're going to apply them a bit to an actual scenario where we might want to, say, calculate the hydrogen bonds. So this example is an example of an actual analysis that you might want to run. Although we actually do have a hydrogen bonds analysis module in MDAnalysis. This is an example of something that you could write by yourself if you wanted to customize it in any way. So in this example, what we want to do is identify hydrogen bonds between specific residues and the water solvent. And I guess there's a few ways that you can define a hydrogen bond, but for the purposes of this example, we'll just be using geometric criteria. So, a hydrogen bond typically has an acceptor that's attracting the hydrogen, the actual hydrogen, and the atom that's donating the hydrogen. And in deciding what is and isn't a hydrogen bond, we'll just use a distance criterion of 3 angstroms and an angle criterion of being greater than 120 degrees. So if we leave adenylate kinase for a bit and we go back to a PEG chain of water, we can select our oxygen atoms in the PEG universe. And again, we just know beforehand that these have the types OS and OH. And then let's see, how many waters do we have? Okay, 21. We can also select the hydrogens from those waters. And is that correct? I wonder if there's a solvent involved. Okay. not actually sure what the waters are called here. Every now and then, it's called what? Okay, we do have 4,000 waters. In that case, I wonder where these acceptors are coming from. Oh, they're from the peg. That makes a lot more sense. All right. Sorry, that was a brief diversion into insanity. These acceptors are not coming from waters. Alrighty. And okay, our peg is called UNL for some reason. Alrighty. So we've selected possible acceptors inside the peg chain. We've accepted hydrogens from water. And what we want to do is we want to find the hydrogens or the waters close enough to peg to possibly hydrogen bond with it. And to do that, we can use the distance array, which takes us 1.64 milliseconds. But that being said, given that we know that the hydrogen bonds have to be close to the peg chain, we can use cap distance instead. So I'll keep running through this particular part where we use the naive distance array. We can use the criterion where the distance is less than 3 angstroms to create kind of like a Boolean mask. And from there, we can get the indices of where it's true, where the distance is less than 3 angstroms is true with numpy.where. And that returns us 2 different sets of indices, again, in the order that we put into the distance array. So the first array of indices is the acceptor indices, and the second array is hydrogen indices. But like I said earlier, what we can do instead is use cap distance. So if we use cap distances instead, how long does this take? 3 milliseconds compared to 1 millisecond. Okay. In this particular case, it seems to have taken a bit longer. But again, for much larger sets of atoms, this should be the more efficient function. In this case, we return indices and distances. What we can do if we're only interested in the indices, because we know that we set the max cutoff to 3, is set return distances to false. Oops. And set that to indices. So much like the numpy.where function earlier, if you look at the raw indices object returned, this is an array. This gives you the indices of the atoms or the positions that fulfill this criteria. But unlike the numpy.where function earlier, it's not kind of nicely laid out for you. It's more of an array where you have 2 columns, where the first column is, like you introduced earlier, the index into the first set of positions, and the second column is an index into the second set of positions. This is sometimes helpful because if you just want to look at the first pair, you can index like this. But here, when we just want the acceptor indices and the hydrogen indices, what we actually have to do is transpose it to get the same results as we got with numpy.where. So here, I will transpose, and again, we can have a look, and it's a flat array of indices. As Fiona showed earlier, we can use indices to create atom groups by slicing other atom groups. So what we can do with these indices now is create new ones from our larger pools of possible acceptors and possible hydrogens with these indices, which is what we do here. And you might notice that some of these have repeated numbers. What that just means is that in our output atom group, we'll have 4 copies of the first atom, which can be quite helpful for if we want to do pairwise analyses after. So I'll run this. And again, we can check that the length of these potential H1 acceptors is 57, and the length of the indices is also 57. So now we have potential acceptors and hydrogen bonds. We still need to get our potential donors. And to do that, we can use the fact that hydrogens will be bonded to these and only have 1 covalent bond. So this is kind of using the same trick that I showed earlier, using a sum to create an atom group. And this is a list comprehension that loops over all the hydrogens, sorry, that we created earlier. And we look at the bonded atoms for each one. So if your universe has bonds, each atom that you look at, this being an atom, will have an attribute called bonded atoms. That is in itself an atom group of things that are bonded to it covalently. And you can also index these. If we look at these particular hydrogen bond atoms, we can look at these bonded atoms as well. And unexpectedly, we actually see that there are two atoms here. So for some reason, well, I'll explain this reason, but unexpectedly, it looks like this hydrogen is bonded to the oxygen and another hydrogen. This is probably because there is this water has been simulated with a constraint, and the constraint has just been interpreted as a bond. So again, we know this because we've been looking at the universe, and so we only take the first bonded atom, which we know is the oxygen. But it's always a bit wise to check what you're actually working with before assuming that kind of thing. Right. So now that I've gone through all that, we can get our hydrogen donors, or possible hydrogen donors, by using the sum. So now that we have a pool of potential hydrogen bond donors and hydrogen bond acceptors, we can apply our second criteria, the angle, which I think if we, I know it says here, we have decided has to be greater than 120 degrees. So again, we can use this calc angles function that I showed earlier. We can pass in these arrays, which have all the same shapes. And we can convert the output, which is radians, into degrees. If we have a look at the angles, we can see they kind of run the gamut between, what's the minimum? Between 56 to 178. So again, we can use a mask, we can use numpy.where, and just get the angles that are greater than 120 degrees. And again, this will be the same, this will be an index into the possible angles array that we saw before. So we use these indices of fulfilling the angle criteria to again slice our possible hydrogen bond groups. And we've decided now that these are the atoms that fulfill the criteria for being close enough and at a great enough angle to be involved in a hydrogen bond. And let's see, how many do we get? We have 33 hydrogen bond acceptors. Okay, the notes say that we have 21. I'm not sure which one is the correct one or the incorrect one, but sure, that sounds a bit plausible to me. And yeah, that's kind of, I guess, how you could step by step write or run through a hydrogen bond analysis. So there's an exercise here where we put all of the above into a function. This kind of ties into, I think, a question that someone asked earlier, where the typical workflow in using MDAnalysis is often to prototype code step by step, the way that we did here. And then once we're happy with it and we sense checked it and checked that everything makes sense, we can just bundle it all together into a single function and I guess use it in a script. So this exercise is kind of getting you to do that same thing, where you take in as input a group, an atom group of hydrogens, an atom group of acceptors, and we return smaller atom groups of the atoms actually involved in the hydrogen bonds. How am I doing for time? There's a bit more. I might not run through this. I think this is fairly, you are pretty much just bundling the above code into a single function. I might move on and we can come back to this at the end. But it would be a good idea. But once you have written it, you can check your function by running it on the same hydrogens and acceptors and groups that we selected kind of all the way back at the start. So to recap, so far in this tutorial, we've kind of shown uses of the distance array function that takes two atom groups where they don't have to contain the same number of atoms. I'm not just sure if we've shown the self-distance array function, but if we wanted to, that would only take one atom group and calculate all the distances within those. And we've also shown usage of the capped versions that only considers atoms within a certain distance threshold. All right, so that was a lot of analysis on using distances and things on, I guess, static positions, on positions that were loaded in a single frame. But for most of us, we are trying to run analyses on trajectories. So this next section of the tutorial focuses pretty much on those trajectories and frames, how they work, what's going on under the hood, and a few pitfalls that people often run into. So firstly, we can load a trajectory the same way that we've been loading our other data in the previous examples. Here, we're just going to load from the test data files, the PSF and DCD example that Fiona showed earlier, with the ADK protein. So the trajectory functionality is mostly focused around the trajectory attribute or object assigned to this attribute. Where under the hood, each is actually kind of a fairly format-specific reader that indexes the file typically that you have on disk. So for example, because this is a DCD file, we're using the DCD reader. If I wanted to create a different universe with GROMACS files, this would instead be an XTC reader. And this includes a bit of information about the trajectory itself. For example, the XTC trajectory is much shorter, it's only 10 frames, but it actually includes solvent, so it has a lot more atoms. So this trajectory object has a length in frames and a time unit of picoseconds. And there's a link to more about the base units in the documentation. So we can have a look at the attributes of the useful attributes of the trajectory directly. So for example, the number of frames, although I think you can also just go length. Yeah, and that will give you the same result. Oh, okay, that was in Excel. We can also get the time between frames with DT. So to be clear, that's not, when you're simulating, you have to specify a time step. This is not that time step. This is the time between the output frames that you've chosen to save. And in many cases, people only choose to save, say, every 100th or 1,000th frame, just because that saves a lot of disk space. And in this case, it's about 1 picosecond. We can also calculate the total time of the simulation loaded, where here it's 97 picoseconds. Within the trajectory itself is the time step object. This is called TS, and this holds trajectory information specific to the current frame. So mostly that includes the frame number, the time, the dimensions, so your cell can also evolve over a trajectory, and of course the positions. And that's how it's represented. So there are no cells showing that, but I guess you can just have a look at that directly yourself. Time, frame, and so on. And now we can go on to the actual important part and for most users, which is moving through a trajectory. So up until now, like I said, I've only been showing what we can do with a single frame of the trajectory object. And by default, when you first create your universe, this will be the first frame. We can traverse through the trajectory in a couple of different ways. So firstly, what we can do is we can show random access. So for example, if we create an atom group for the first 2 atoms in the universe, and we look at the positions, that's where they are in the first frame, which is currently loaded. With random access, you can pass any index to the trajectory and it will move to that frame. So if we wanted the 7th frame, for example, we would just index 6 and it returns a time step object, kind of verifying that you're at time step 6. And we can look at the current frame also being 6. The positions themselves will actually also update. So this is a trap, I think, that a lot of people don't realize, that the positions attribute of an atom group is not static and that it does update as you change frames. So this can be both a good thing and a bad thing. It mostly just depends on how you choose to use it. This also means that anything that you change with the positions are temporary. So for example, if we go back to the first frame and we do something to the positions, say we set them to 0, and we change to a different frame, those changes will not be saved. So if we look at the first frame positions here, the cell, we go back to frame 1, we look at the positions, and we set them to 0. It kind of looks like, while we're on this frame, like this function has worked. However, if we go now to the second last frame, the positions are what they would be in the second last frame. And if we go back to frame 0, we see that these positions are exactly the same as they were before. The zeroing has not persisted throughout this change. What you can do, if this is difficult to work with, is you can assign a new array of positions. So if I go, let's just make sure I'm in frames 1, positions equals first 2 atoms. We can print firstly the positions array. And we can print the first 2 atom positions as the attribute of the atom group. And then we can go to a different frame. Let's go back to the 7th frame, and we can print these again. Maybe I should have printed. So here, the 2 arrays are the same. As you would expect, I've just assigned positions to this positions array. Here, they, well, maybe I should start with this one. Here, the positions array as an attribute of the atom group has updated, as you would expect, because you've changed frame. But because I assigned that array to this new variable, this has not updated with the change in time. So if you want those positions to persist throughout your analysis, that's the way you would do it. This kind of ties into, I guess, what goes on under the hood and what actually happens when you go atom group dot positions. So I might explain this exercise first. It's quite relevant to this exercise, and then go back to what the arrays are. So if you print this code in a cell, what it does is first it checks for equality. It checks, are these values, is the left equal to the right? And then it checks whether an object in memory is the same thing as another object in memory. So these are often very similar answers, but not always. So if we run the cell, what we see is the answer is true, as you would expect. Left is equal to right because they're exactly the same thing. However, if we ask, is this array the same object in memory as this other array? The answer is actually false. And what's actually happening is every time you call the positions, it's actually returning you a copy of that array. And that's just to make sure that you don't accidentally, I guess, mess with the positions under the hood. This is generally more robust, but this can definitely trip people up. And this also has a lot of implications for example, making changes to the array. So if I wanted to set all my Z positions to 0, I can do that inside the array by indexing the 3rd column. I can print those positions. Oh, well, Well, to make it clearer what I expect to happen first, let me assign this to positions again. Normally, when you're working with an array, you would expect it to have done what you told it to do and to set this column to 0. If you try and do this again by accessing the positions attribute of the atom group, it's not going to work. It's going to return you the array again as a copy. And that's because what you've done is you've made these changes to a copy, and this is returning you a copy of the original object. So I guess how might you get around this? Sometimes you really do want to edit the positions and have that actually have effect. This is an exercise, and this is a bit of a tricky one. So I might get you to experiment with that yourself for a few minutes, and then I'll come back and talk through the solution. Okay. I've been given a 10-minute warning, so I might get back to the notebook, and we can come back to this at the end if there are any questions about this. But basically, what you would do if you wanted to get around this is to make use of being able to assign positions as an array. So it involves this trick firstly, which is assigning the positions array to a new variable to make sure that we get a copy. So let's do that. And let's do this as well. Just set the Z column to 0. And we can have a look at our positions, make sure that we've actually done that. That's right. If we wanted to make sure that the first 2 atoms positions also updated, what we would have to do is manually set that to this new positions array. And what that will do for you is now the original positions that get returned to you as a copy when you call this positions attribute has now been replaced with this positions array. So if you change the frame, this will obviously update, but while you stay in the same frame, the Z coordinate of these first 2 atoms will be 0. And there should be a solution cell that kind of goes into that and explains the solution maybe in a bit more detail. Cool. So now that we've, I guess, cleared up, I think one of the great mysteries of why people sometimes get some really weird errors in MDAnalysis, let's move on to how we can iterate through the trajectory in different ways. So I've already shown random access where we go to a specific frame, but what's very common is that you want to apply analysis to all the frames, or at least to regularly spaced frames. So what we can do is we can just treat the trajectory as an iterator, and we can just go through it in a for loop. So this is an example task of what we could do, and is just to get a list of all the times in our trajectory. If we iterate through the frame, we get all the times corresponding to, sorry, if we iterate through the trajectory, we get all the times corresponding to the frame. If, for example, we don't want to go through the entire trajectory, we only want to say, go through a very small subset and maybe every 3rd frame, we can use the slicing notation or functionality that is common to Python. So what we're doing here is we're treating the trajectory a bit like an array, and we're slicing it from the 2nd frame using the start index of 1. We're going to, I think, the 2nd last frame, and we're only taking every 2nd frame within that subset of the start and the end. So to make it a bit clearer, we can do the same thing that we did before, just show the times. And you can see kind of that it starts from a value of 2, whereas the first value is only 1. And it makes jumps of 2 throughout the rest of the trajectory. There's another exercise here that kind of is really more of an exercise of slicing more than anything, and that's to create a reverse list of the trajectory times. Obviously, what you could do is you could just reverse the list itself. But what you can also do is reverse the trajectory. Using the same slice notation. So this is, again, starting from the start, going to the end is the default arguments when you don't have anything on either side of these columns. And the -1 means we're moving through the trajectory backwards. And instead, we can do it this way. So we're counting 97, 96, 95, and so on. And I believe that should be the solution in the cell. Yeah. Right, so now that we kind of know how to work with trajectories and how to iterate through them, we can kind of combine everything that we've done in this notebook so far, doing an analysis on a single frame, iterating through trajectories, and we can run an analysis on every frame of a trajectory. So we probably won't do the hydrogen bond analysis example that we showed earlier. It's a bit involved, but what we can do is call a radius of gyration or gyration, sorry, function again. So on the PEG molecule, if we only want to look at the oxygens again, we can calculate the radius of gyration of those oxygens for every frame in the trajectory by looping over it and append it to this list. And we can then plot that list and show that the molecule is probably going, and getting more compact when it's lower and less compact when it's higher. We can also go back to the adenylate kinase example and see what happens to the angles between domains as we iterate over the trajectory. What this will be again is this is the more involved example of above. But if we go through the pseudocode instead of just running through it, it's we can create some empty lists as placeholders to hold our results. For each time frame in the trajectory, we can calculate these angles and append them to the lists above. So yeah, we could run through this. I think given the time constraints, I'll probably just cheat a bit. Feel free to do this on your own, but I'm just going to execute the cell that has the solution instead. This is just a copy and paste of the code that was up earlier. Again, we're defining the centers of geometry of our domains that we care about. We're calculating the angles, and we're just appending those angles to a list. So let's just do that. And with those angles, we can now plot over time. We can see that, well, the angles grow. So the distances, so the domains are kind of moving further and further apart. And this is probably quite a nice graphic to visualize, in some aspects, your conformational transition. Right, so that's the end of this tutorial. Going a bit more in depth into the distances functions of MDAnalysis, what you can do with them, and also the trajectory functionality. Does anyone have any questions on this part? If not, oops. It might be, okay, I've accidentally stopped screen sharing. But yeah, it's probably a good time for this. This is now our scheduled question and answer section or break time before we move on to the molecular nodes and blender part of the workshop. So this is again a 5-minute break. Feel free to ask any questions or just get up, get some water, and we'll see you in 5 minutes.
So I'm going to be taking the next section for something a little bit different. I'm going to be talking about a program called Blender, an add-on that I created for that program called Molecular Nodes, and how we can take some of our some of the data that we've been working with and make some. God, my webcam is just going absolutely wild. I have no idea what's going on there. So how we can take some of that data and make some really pretty movies with it. And so I don't have slides to begin with. but everything I'll be talking through is in the repo under the molecular nodes tutorial. So it's all written up in this markdown document. So everything I'll be covering today should be written up in here. If you miss something, hopefully the details are in there so that you can either watch the recording or follow along later in your own pace. This will link to the actual documentation for the add-on, which again does have lots more tutorials and information on all sorts of stuff, which you can find there. As a very quick, brief overview, if you're unfamiliar, Blender is this fantastic 3D program that people use to make TV shows, movies, games, all sorts of fantastic things. You can render anything your heart desires and make all sorts of really cool art. And the molecular nodes add-on basically brings protein structures, molecular dynamics, trajectories into Blender, so we can take advantage of all this beautiful rendering power and animation to make really, really nice videos of our trajectories, either for colleagues or for sort of the general public who may not be familiar with what we're dealing with. And I link to it in my documentation. I also have a bunch more tutorials on YouTube, etc. So we're going to be just working through this. If you have Blender installed, you manage to follow the instructions and have molecular nodes installed, I don't really have time to troubleshoot installation. So if you did have some trouble, then maybe follow up with me afterwards and rewatch this tutorial. But this is the screen you'll be greeted with when we start up Blender. And if I don't click on anything here and I just sort of click here, then we can see it's this big open empty gray scene, but this isn't set up. So this is like an empty starting spot, but we can change this and tweak it, and molecular nodes comes with basically a template to make sure that the 3D scene we're dealing with is a bit more set up, ready to go for doing molecular stuff, and that's should be here. So that's this molecular nodes new file. And so if I click on that, we'll see that we've gotten a setup that looks like this. And again, this is described in the instructions, and I sort of detail what's going on here, what's what. Blender, there's a lot inside of Blender. As you can see, there's buttons up here, there's buttons down here, there's buttons everywhere. So it's quite easy to get a bit overwhelmed, and that's just because Blender is so ludicrously powerful. It can do so many things. It's made for everything. I have managed to sort of massage it and tweak it so that we can do molecular stuff inside of it, but everything else is still possible, which is why there's so many options. We're only going to deal with a small subset of those options. The sort of viewport we can see here, we can see this sort of 3D scene. We can see a blank space here and this blank space here. To get sort of started and just start dealing with molecular things as soon as possible, we should see this molecular nodes tab down here. And so all of this you can resize. You can sort of click and drag to resize things, which I'm just going to do here to make it a bit more obvious. But we've got this molecular nodes tab. And so by default, it's set up ready to download from the PDB. We're not going to do that today. We're just going to change over to importing a molecular dynamics trajectory. And so I'm going to select that, and it's going to change, and we're going to be greeted by this scene. And so the reason we're sort of doing this joint workshop is that molecular nodes uses MDAnalysis under the hood to read the trajectory, import it, update it on the fly, and do all this sort of fancy rendering. And so it's quite tightly coupled. And Yuxuan's going to show off how you can have that tightly coupled to a Jupyter notebook at the same time. We're not going to go through in detail in that, but we're just going to sort of show off that that's something that's a work in progress that we're working towards. But what I'm going to do is you just need to select your topology in your trajectory file. As an example, I'm going to be using the MDAnalysis example data. So in the notes, it sort of mentions that it's this data set here, which if you were following along with Lily's notebook in the previous tutorial, you should have this already downloaded, this data set. If you have your own data set, feel free to sort of use that data set as well. But I'm just going to select go through and find my topology. So I've got my topology here. I'm going to find my trajectory and use one of these trajectories here. And so I'm going to give people a couple of seconds, a minute or so, to make sure that they've got their topology and trajectory selected. If when you're opening a file, sometimes relative file paths get a bit broken. So this, if we click this sort of cog, this might be turned on and you might have sort of relative file paths. It's a bug at the moment that this can be kind of broken. So if we just turn that off, we make sure that it's just currently absolute file paths that we're using. And we can give our trajectory a name. Currently it's new trajectory. I'm going to say example trajectory. And you'll see as I'm typing on my keyboard, you'll see all the keys that I press show up for a couple of seconds. I'll try and say them as I do them, but if I do something and I don't say it, it'll show up and it will be on the recording. So you can see, oh, he pressed this key and that key to get what he's after. And so we've got our information selected. You can change the style that you start with. This can all be changed after the fact. I'm just going to leave it on spheres. We can use the MDAnalysis selection language. So what we were learning in our notebooks earlier, where you can say res name this, res blah, 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 to either filter the trajectory or add some selections. So by default, it imports all, but I could change this to res name, tyrosine, etc., to sort of filter the atoms when they're imported. By default, we use MDAnalysis to stream the trajectory from disk, so we don't load it all into memory, and we keep a live MDAnalysis session in the background. If you want to load it all into memory and discard that session, you can turn that on. There are reasons why you'd want to do that. I'm not going to go into it today, so we're just going to leave that off. And you can add some additional selections here so that it would create a Boolean mask for alpha carbons and that sort of thing. And so you can add those. Again, this is the MDAnalysis selection language it uses. But again, I'm not going to go into detail on that today. So I've got all of that input and I'm just going to hit load. We've got the information at the bottom saying it's loaded in 99 frames. We've got some information. I'm just going to resize that again. And we can see something has appeared here. Something has appeared here. And so now we can get into the exciting part of starting to look at our universe. In this viewport, again, I have some keys on, I thought I included some notes on moving around. They're in the documentation website at least, but to move around, to change the view, middle mouse button, or if you're on a laptop, 2 fingers on the touchpad will rotate your camera around, or you can left click on this little dial up here. I'm just going to resize this window to make it a bit bigger so we can sort of see what we're doing. So I can click on here, rotate around. You can scroll wheel in and out to zoom in and out, or if you click on this magnifying glass, click and drag, zoom in and out, middle mouse button and shift at the same time. So that's middle mouse button shift will move around, or if you click the hand, you sort of drag around. And we can see there's this big, ugly gray scene. I promised you beautiful lighting and cool renders, and we're looking at this bunch of gray blobs. But there's a few different ways to view things inside of Blender. And so by default, this is the 3D view, which basically doesn't calculate any lighting or anything like that, because sometimes calculating lighting can be very slow and complex. And so we've got our 3D scene. We can change it to a rendered view, so we actually have some calculated lighting, and we can do that by up here, there's 4 different options. One is sort of this wireframe mode, one is previewing, and then one is actually rendered, and we can see it's calculating lights there. I might leave it there for a minute and check if people are getting stuck and if anyone has any particular questions. If this is sort of small and you can't see things up here, you might need to middle mouse button to drag the menu around, or you can resize it to sort of see that. And so we're just changing through different sort of viewing modes. And I'm going to leave that on rendered. And I might just zoom in and so we can see some nice looking atoms while I check to see if people have some questions. Okay. Just questions from earlier. So we've got our trajectory imported. We can see some atoms on our screen, hopefully, and we can see, okay, there's actually some, we got some fancy, nice lighting. Currently, we might notice that our atoms are into the floor. That's all right. We'll fix that in a second. But what I want to sort of drag, what I will do first is fix this. And so while we're looking in this big 3D scene, I might zoom out a bit. And we can see by default, it comes with this big sort of backdrop. If you've done any photography, you might sort of recognize something that looks like this. So we're basically, taking some beautiful portraits of our molecules. But we can left click to select things. And you can see if I left click and select my structure, it goes all orange. If I left click and select this, it goes orange. And you can move these things around with keyboard shortcuts, or if you enable these little gizmos on the left, you can move the sort of structure around. And so I might just move that structure up, or I move this down. We don't have a huge amount of time to sort of go into too much for moving stuff around, and we're not going to worry too much about that today, because we're mostly just looking at a trajectory. But we have, now that's no longer in the floor, we can keep moving on. And I'm just going to resize this a bit so we can sort of get back to how it otherwise is. And so, okay, we have our trajectory imported. What are we looking at? What's going on here? And so this is the nodes part of molecular nodes. And what happens when we import a protein structure or a trajectory with topology is that it imports all of the data into Blender as actual atoms with bonds and relationships, etc. And then through these nodes, it computes different styles, it assigns colors. In this case, it creates a sphere for each atom. And we can change how we interact with that. And so we read this from left to right. We can see this group input. This is where the data comes in. I'm just left clicking and dragging to move these around. The data comes in here. It goes out. Can go back up. It goes out through here. And you can see it's going through these 2 nodes here. So we're color set and style spheres. And so if I actually just skip all of this, now the data is just coming in here and going straight back out. We can see what we have is just the underlying topology information. So I might go to resize that. So we can see our underlying topology information. If we then go through this node, which assigns colors, these atoms now have a color assigned to them, but still it's just sort of topology information. If we then go through this node, now it assigns a style to them, which I need to be in rendered view to see. And so in this case, we're assigning the style of spheres, but we might change to something else. And so I'm going to change to a ribbon style. So to do that, you need to add a new node to the scene. You can use this menu here to add, or you can also use Shift A to open the add menu. And you'll see lots of things come up. All of these are different nodes you can use to do in Blender all sorts of stuff. None of these are particularly well suited for, say, doing things with molecular stuff. But down here at the bottom, molecular nodes, I created all of these nodes specifically for working with molecular data. And so we can see there's a bunch of selection stuff, animation, all these sorts of different things. We're just going to go style, and I'm going to select a ribbon. It's going to give me a new node called style ribbon. And then instead of this one, I'm just going to plug that in there and plug that in there. And so now we can see, okay, rather than styling like atoms, we're now styling as a ribbon. And you can see there's a few different dials for different sort of settings, where if I change that, it updates live the sort of style that's being applied. And the same thing does happen with the spheres as well, where if I plug that in and change the radii, it scales the radii. There's a few different sort of options that you can play around with. To change the styling. And so this is, again, the data is flowing in through here, flowing out through here, and depending, think of it like pipes. The data can flow into this node, and then it flows sort of into both of these, but this has nowhere to go, so nothing happens. But this one, the data flows out, and so this is the node that's applied. But if I change that, the data now flows through here instead. And I do have a question. Cannot see topology and trajectory files in MDAnalysis. Manually download. I'm not sure about manually downloading the files. Oh, there we go. But any trajectory, anything that MDAnalysis can read in terms of topology and trajectory should be able to be read by Blender as well. So we've got information flowing through, we've got our topology, and we're applying some stuff on top. But the whole point of what we're trying to do here is that we want to do this onto a trajectory file. So our simulation, we want to show off that data. And so at the bottom here, you might notice this sort of weird looking box down here, and this is called a timeline. And so you can see if I click and drag that, what this does is it moves through the trajectory that we've imported. And we can see that our style, our trajectory is updating there. And so if I go all the way up to past 100, you'll notice that nothing happens because this trajectory had 99 frames in it. And we start at frame 0. And so once I go past 98, it just stops updating. But our sort of frames down here, this is our trajectory, and we can see it sort of playing back as we do that there. And if I, again, skip all of that, we can see, okay, it's the actual underlying atoms that are moving. And we can apply one of those styles to it, and then it's updating as we sort of go through like that. Represent ribbon style similar to Chimera X, where we see different secondary structures. So you can have cartoons where you have your alpha helices and your beta sheets. The problem with that is you need secondary structure computations to be able to describe that. When you download from the PDB, if you're importing a protein from the PDB, it will have that information, and you'll be able to use one of the nodes is style cartoon. And so this, if it had secondary structure information, would show a cartoon with your alpha helices and your beta sheets. But I don't have, as part of molecular nodes, secondary structure calculations. There's talk of MDAnalysis having that at some point, maybe. And so if MDAnalysis can do that sort of on-the-fly secondary structure calculation, that can potentially then be a part of it. But at the moment, that is a limiting factor for a trajectory, is that we don't have per frame calculations of secondary structure. I might just delete that one. So where are we at? We're at 1, 2. So we have our style, we have our trajectory playing back. How do we actually make an image or render an image? I'm going to maybe switch back to these spheres and ensure that I change over to this nice rendered view so I can see everything. How do I actually save an image? If you're used to using a program like PyMol or Chimera, you just basically position yourself where you want the image, and then you say like save image or something like that. That's not how Blender works. It may seem unintuitive at first that, oh, I want an image of what I'm looking at. But Blender works through a camera. So if I zoom out, you'll see there's this big thing over here. This is my camera, and this is what it's looking at. And if I have a look at the outliner up here, we can see this is my example trajectory. Here's my camera. There's a few other things you'll see in this props. There's this backdrop that's sort of sitting here. But this camera is what's responsible for actually rendering an image. And so to see what the camera is going to see, if you click this little toggle camera view button, it will go into the camera and we can see what the camera is seeing. And we can see, all right, now that we're inside the camera, we're getting some extra special little lighting calculations where you're getting this nice depth of field effect. And so I might grab my trajectory, just move it up slightly. And okay, this is what my camera is seeing. Everything inside this box will be rendered. If I go up here to the top left, there's a render tab. There's a couple of options, render image, render animation, etc. And I'm just going to click render image. And so that just renders a still image of whatever your camera is currently looking at. So if I click that, it starts calculating, and you'll see that it goes all fuzzy, and then it slowly gets less and less fuzzy over time. This is a, just going to zoom in so you can see in all its glory. So Blender renders things via what's known as ray tracing, which is how it gets this such beautiful looking lighting, which means it has to calculate every single individual ray of light and what it's going to bounce off and where it's going to go and blah, 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 blah. And this is a very computationally intensive process to trace all of these rays, but it results in very, very photorealistic lighting. Now, we're dealing with molecules, so photorealistic is a meaningless term, but we get this nice lighting effect that our brains are basically trained from decades of being alive of how to understand. So a 3D model in something like PyMol or Chimera, you can sort of see stuff and you can pass some of it, and if you've done years of training, you sort of start understanding what's going on. But everyone knows depth of field, everyone knows lighting and shadow and all this sort of stuff, because that's how we see and perceive the world. And so it's very effective to sort of show people, especially non-experts, images of proteins like this, because it has all this visual language that we're used to working with. And we've got a question in the chat. Is it possible to alternate between orthographic and perspective? It is. I can show you that in a second. So we've rendered our image. If I quit out of that and just say render image again, you can see up in the top left, it says sample 44 out of 256, and that sample count's going up. So that's all the rays that it's tracing. And it gives you sort of a time estimate of how long it's going to take to render. And so for me, because I have a relatively powerful computer that I spent far too much money on, it takes not too long to sort of go through and render. If you're on a sort of smaller laptop, then it's just going to take longer and longer. With Blender, it's basically the more money you throw at your computer, the faster it goes. If you play around with it and you're like, oh, you can set something up on your computer and you can then send it off to a compute cluster. So if you have access to a compute cluster, then you can render headlessly via the command line. And so you can ship it off to render there and you just work on your little laptop. So I know quite a few people who do that sort of thing as well, if you're struggling with access to compute resources. But this is how we sort of render an image. So if you have something in your scene, have something that can be seen via your camera, and you go render image or F12, you will have an image that gets rendered. Hopefully the default settings are somewhat okay if the template was set up right. Once you have this image, if you want to save it, you can go image and you can save and save as, and we can save as a PNG or a JPEG, etc. And so that is the basics of how you import and render an image of a trajectory. And like I was saying earlier with our nodes, well, maybe I want actually a ribbon style of my trajectory, and I'll increase the quality and tweak the radius. And now if I click render image, now we've got this nice looking ribbon of my trajectory. And again, this is all dependent on your trajectory. So, actually I want this frame of my trajectory. I can dial that around and I'm happy with that. And I can say render image. And that's how we render images of structures. Now I might give it a couple of minutes to give people a bit of time to play around. Hopefully people are playing around. We'll just drink some water. And someone asked about orthographic and perspective as well. You'll see there's this enormous list of settings and stuff over here. This list does change depending on what you have selected. So currently I have this trajectory selected, and so a couple of things are here. If I select this camera, this list then updates as well. And we can see there's this little camera data. And so under here, there's perspective, or you can change to orthographic if you want no perspective, which may or may not be sort of more accurate for the molecular scales. Or you can also change to panoramic if you want to render for like a dome or something, all those sorts of things. So if you ever want to sort of change the setting of one particular thing, you'll need to select it and change the setting. But that gets it in a bit more into the nitty gritty than I sort of want to do too much today. So I'm just going to go back to the molecular nodes tab by clicking this little thing here and seeing there. So what I'm going to do is show you how to do selections, to combine styles, and then show you how to render an animation. We won't have time to actually render the animation because we saw maybe a single frame for me took 15 seconds. So 250 frames will take, several minutes and etc. But I'll sort of show you how to render one or two, and that should mostly sort of wrap up what I'm sort of showing. What I want to do is, okay, I want my backbone to be this ribbon, and I want my side chains to be ball and stick, let's say, rather than spheres. So what I want to do is I want to either add or Shift A to add molecular nodes style, and I'm going to say ball and stick. And I'm going to take this sphere and press X to delete, or you can also press delete to delete. But okay, I have my ribbon, I have ball and stick. What I want is my ball and stick to just be applied to the side chains. And so this is where selections come in. And you might notice that these different dials all have an input. And these inputs are different colors. Again, I don't have too much time to sort of go into detail with them, but this pinkish purple selection is a Boolean, true, false. So the same way you mask, say, a NumPy array, or we were making selections earlier in MDAnalysis, that's the same concept. This green is an integer, this is a float, etc. But what we want is we want to take a selection and plug it into here that limits it to just the side chains. And so if I say select molecular nodes, selections, side chain, although, I'm realizing you will have a slightly different version to me. Whoops. There should be an attribute or a backbone node. Your backbone node, I think, will be slightly different to mine, but there should be sort of is backbone or is side chain. And we can selection plug that in, and we can see it then limits that ball and stick to just the selection that we plugged in. And so this is sort of how you apply a selection to something, is you get these nodes which output this pinkish purple Boolean, true, false, and we plug that in. And we want to join these two together. So when we shift A, we want a node that joins them together. When you do shift A, you can go through the menus and find them, or you can also just click search. Or if you just start typing, it will search. So I want shift A, join geometry. And so it'll give me this node called join geometry, which will let us combine several things together. And so I have one style, which is applying a ribbon, one style, which is applying a ball and stick, which is limited to just the side chains, and then I'm joining them both together and outputting the result. And that gives me this result here. And again, I want to maybe adjust the style, so I'll change the radius of the backbone, maybe change the radius of the ball and stick. And I'm going to hit render image. And we have our sort of rendered image of our structure. And so we can see everything's applied. And again, if we update the frame of our current timeline, then it will also update what is the style that we're sort of seeing. Now, if I go out of this camera or even just in the camera, the protein is sort of facing away from me. And so I want to turn it around so that when the domain opens up, I want to be able to see it. And again, with these, they're called gizmos. If you turn these on, there will be this one here. It lets you rotate stuff. So if let's go. If I sort of click and drag on this, it'll rotate around. And we can see, if I click on just the sort of red, it'll go just on that axis, the x-axis, or that axis, or that axis. I'm just going to Control Z to undo some of those, but I rotate it around and say, okay, that's what I want facing me. And now when I play back the trajectory, we can see the domain is opening up towards the camera, because that's sort of what we want to highlight from this trajectory. And I might even just do render image just to check on the result. I'll show you. So this is sort of an example rendered animation of this very trajectory. So we've got these two amino acids that are sort of holding on for dear life as they get pulled apart. But we sort of zoom in, we focus on them. Importantly, in things where in molecular software where you sort of use your depth of field with the fog, you lose context of what's going on around you. But here we're focused in on just these two residues, but we can still see the rest of the protein in the background because it's all blurred out. And our brains are used to seeing these sort of out of focus stuff. So we can sort of watch these residues interact as they're pulled apart, but we still sort of maintain all this sort of depth of field. Now, again, we won't get time to make all of this, but you can sort of see the backbone, the side chain, and then it's just a matter of sort of getting your camera right and setting it up to sort of get everything. I'll sort of show a quick example. So we've got our something set up. We have our trajectory that plays back. How do we change some colors? I might quickly change colors, quickly show you how to render an animation, and then Yuxuan's going to demo some notebook stuff as well. So the sort of final area of the starting interface that we haven't used yet is down here. This is called materials. And again, if we have this selected, you'll notice there's nodes. And if I click and select maybe the backdrop, you'll notice that this is also nodes. And so these are called material nodes. And the reason we have to use materials is when I was first learning 3D, one of the more complex ideas to get your head around is that in regular molecular software, you're like, oh, I want to make this protein red. How do I make it red? And things aren't red because we're dealing with a photorealistic ray traced rendering engine inside of Blender. Things aren't one color. If we look at like my skin, it's sort of whitish, pinkish, but the light goes into and under my skin a little bit, bounces around, becomes a bit more red, a bit more blue if it's on a vein, and then it comes out. There's a bit of a sheen, some gloss. Nothing is ever one color. Things have all these different sort of attributes and physical lighting attributes about them. And this is all done through in Blender called something called materials, which is what we sort of see. This is how you control it. And the same idea with molecular nodes, where you sort of have data that flows from left to right and is output. If I select this backdrop, we can see, okay, this is the material and the data for that material flows out to the right. We don't necessarily have data coming in from the left, but we have sort of the result flowing out to the right. And we can see this is called backdrop, and these are all the different options for the material. If we sort of click and look at them, and again, we don't have necessarily time to go into any of it, but thankfully you can relatively simply sort of change the color of something. So in this case, I'm going to change it maybe slightly red, sort of make it pop. But you could also, make it more metallic, make it less rough, so that if I move that, we get some like reflections coming off it. Or you can change all these different things. And I highly recommend just spending some time playing around with materials and coming up with funky stuff. But for this, I'm just going to change this to maybe a kind of orangey for the backdrop. And if we have the protein selected, and we zoom in over here, we'll see there's a material tab for each of the nodes. And so they are currently applying the default material. And so if we want to have a look at that, we can say in this material area, if we click this little drop down, this is the default material. And so we can see the data coming in is the color that's assigned here, and then applying the material if I wanted to, I could take the ribbon and change the material to one of the defaults that I've included called Squishy, which just kind of makes it, if I click render, looks kind of like biological and soft and squishy looking, which is an effect that a lot of people go for when rendering like biological molecules. Again, I mean, it's all meaningless at this scale, so why not have a bit of artistic fun with it? But you can see, all right, we have different materials for the ribbon and the side chains. And so when you set up a style, there'll be a material that's applied. By default, it will always be default, but you can change it over to something else. And then the material will get color information that's set up here. I don't have time to go into it today. There's plenty of examples in my documentation of how to do all of that. But then once it's in the material, it goes through all of this and you can tweak that here. And so let's say we're happy with this. We've got our animation that plays back. It's nice and squishy and gross looking, which is exactly what we're after. And we want to render our animation. So if I was to render this animation, it would render these frames, hit here, it would freeze, and then it would continue rendering frames all the way up to 250, and it would just be a bunch of nothing happening. And so what we want to do is we want to adjust our start and end, which you can see here. So this sort of displays our current frame. If I adjust this little playhead, that's our current frame. This is our start frame and our end. So we actually want to adjust our start frame to 0 because our 0th frame of the trajectory will be on 0. And then 98 will be our 99th frame of the trajectory. So if I adjust these two values, now when I sort of drag through, it'll only be playing back. And you can click play or pause, or you can also press space to play or pause. And we can see our sort of trajectory is playing back like this. And you could, if you want, just sort of render animation, and that will just straight away go through and render the animation each frame. But we want to maybe tweak the output settings before we do anything. And the best way to do that is with this little printer. So if I mouse over, it's output properties. And so this is the resolution. So currently it's 1080p, 1920 by 1080. Frame range is here. And importantly, the output folder. By default, it's a temporary folder, but we can change that to, I don't know, the desktop if you want. And it will save. Again, by default, it renders a still image for each frame. So in this case, it will render a PNG per frame, and then you would combine them all into a movie. That is the recommended way, and I would highly recommend doing that. You can render straight to a, I can't even see, like a video, FFmpeg video. But if you get, 60% of the way through the render, something happens and Blender crashes, your video file will be corrupted and you can not finish rendering the rest of the animation. So I recommend rendering as PNGs and then joining them together. You can use Blender to do that. You can use any video editing software to join a bunch of still images into a movie. Because that way you can get halfway, stop it, and then start again tomorrow. And you can just pick up where you left off, basically. And so you choose your output settings, you choose your output format, and then once you're happy, you just render animation or Control F12. So as an example, I'll click Control F12, and so it started rendering. It's going through sampling up to 256, and then it's going to move on to the next frame. And so now it was on frame 0, now it's on frame 1, and so it's going to keep doing this for the next 20, 30 minutes while it's rendering that and acting as a space heater in my bedroom. And you can sort of press escape to cancel that rendering animation. And that's how you would render an animation. And so that's just sort of going to show this domain opening up and just have a nice rendering of it. you can move your camera around, you can, zoom it in and out, you can have your protein start over here and then move over here. You can do all sorts of different stuff. Don't really have time to go into any of that. Again, there's documentation on the website along with video tutorials there. But hopefully that has been enough to hopefully maybe get people started. There are a few questions, so I think some people were managing to follow along. Yuxuan's going to show off some using Jupyter Notebook with Blender. But if people are managing to get some renders, we're going to send a link that hopefully you can maybe upload them as an example later on, so that when we sort of write up a blog post summarizing the workshop, we can say some people got some cool renders. So hopefully some people got some stuff working. I will... Yeah, that leaves 10 minutes or so for Yuxuan, so I'll stop it there.
Okay, thanks, Brady. So, hi everyone, I'm Yuxuan. I'm currently a postdoc, and I work a lot with MDAnalysis. And so what I'm gonna show you is just some other fun stuff to do too. Sorry, I'm just gonna hide my video panels. So to do with the to do with Blender with MDAnalysis, because theoretically Blender use MDAnalysis under the hood to do all the streaming of the trajectories. So there's one way to actually to use Jupyter Notebooks as a way to interfacing with Blender, and because molecular node is also like a Python module that's installed inside the Python environment inside Blender, you can actually use molecular nodes to serve as a function, as the NGL view to do some interactive visualizations inside the notebooks. Sorry, yes. So I don't really expect you to follow along the notebooks I've been writing, which can also be found actually inside the Git repositories. But this would be one of the plugins that will be used to create a Jupyter kernels that are directly connected to Blenders. So what's eventually will be showed up inside the Jupyter notebook as a kernel will be like something called Blender _ something, which will be the Blender versions. And if I prefer to use VS Code, you can also use VS Code to do this. If you just open a notebook, and you can see if you select this one, select the Jupyter kernels, you can see there's a Blender 4.0.2 already installed in it. So if I open this kernels, Blender, that's huge, Blender instance will be showing up, and you can just click, similarly as what Brady be showing, you can click the molecular nodes. So I will use what's here, what's the import functions here, but I can just use the notebooks here. This one would be the thing that is the stuff that is connecting Blender with Jupyter, would be the API for the Blender, which in my opinion is not that really good coded, but nevertheless, there's also molecular nodes that can be imported, and also you can just use the MDAnalysis modules here. So you can actually change the rendering engines of Blenders as well here if you have a GPU, and you can use Cycle or EV. So as what you normally do, you can load the trajectories using MDAnalysis. So this here, I will be loading the ADK equilibrium simulations that also be downloaded from the MDAnalysis data. And similar to NGView, which I wrote quite similarly as like just to get you familiar with this. So you have a session similar to like a viewer in NGViews. So this will be an empty session. If you load it, it will be the session that's directly connected to Blender, and you can simply just use MDI session to show the universe. So this will work. As you can see here, the universe already showing up here. And if I don't need all this stuff. And okay, so you can So by default, it's showing as the ball, all the hydro, all the balls here. I just click this a little bit, like what I've been showing as well by Brady. Okay, I'm not a guru for Blender, so let's see. Okay, so if you just click play space, you can see the trajectory already synced with that one, and you can pretty much, if you click here, to change the representations of the protein. Like I don't want really to do some fancy rendering here because I'm using a laptop here, so you can see it's pretty nicely rendered. And you can also show the other stuff like atom groups that can be selected using the syntax inside MDAnalysis. So you can select proteins, you can select different residues, and if I click this show one, so some other stuff will be showing up here. So this will be the protein, the residues selected, and the residue 156 that are also selected. So you can change the representations of these residues of these specific instance that are all synced to the universe. So you can see here, now it's all moving together with the trajectories. So this creates a better interface to instead of loading all the stuff and doing the syntax selections inside Blender, you can use Jupyter notebooks as a way to get faster prototyping of your rendering things. So what's more fun to do is you actually use on-the-fly transformations of MDAnalysis. So what this does is it can add different kind of transformation to the trajectories that is not really covered in this workshop, but you can fix the PBC issues or align the proteins to the center of box or whatever that is. So what I'm doing here is something called position averaging. So it's kind of a smoothing machinery to smooth the trajectories. If you see right now, it's kind of quite rigid around. And if add the transformations, you can see it is much more smoother. And also, eventually you can also save this as like a Blender files, and you can open it again and do the same rendering. And you can also move this stuff to, like, you can do some prototyping in your laptop and you can render it as Brady says, you can render it inside your own cluster or someone else clusters. So you can also actually move this stuff around, like, so these are the 4 instances of the atom groups I've been showing here. You can actually grab one of these, you can move this to the other side. Oh, this one is not showing up as a ribbon here. So now you can, you see, you can overlay these 2 stuff. You can just do a quick rotation of this one. So you can show the protein to different orientations, so you can see this movement more clearly in different aspects. And also you can just do a pretty quick rendering of these simulations that are in sync with the trajectories. So these are some basic usage, and just more advanced usage that are still prototyping is kind of one of the our GSOC, Google Summer of Code project. I think Fiona or someone will talk about it later in this workshop. But this is one of the prototypes that you can do some kind of both exploration and also explanations on the simulations or the analysis results. So this will be an example to show the distance in Blender. I won't go through this in details, but what it basically does is it draws a line of 2 different coordinates and also shows like a distance text on that. So this would be like the analysis that you have been using, the distance modules inside MDAnalysis. It captures the distance between the center of mass of residue 33 and 156. And what it does is it can show this distance as well to inside Blender, so you can see here, just like a line. So, yeah. And you can see the number change when the trajectory is evolving. So this is just one of the examples. That's what Blender can do to enhance our understanding of the MD analysis results. And just also, it's possible to have some other analysis classes that can be visualized in a similar way inside Blender. So it creates a better way to to understand what we're actually measuring, not only a single or a NumPy array of numbers. So if you're interested in this aspect of both interfacing between of Blender or MDAnalysis, feel free actually to to keep an eye on our announcement of GSOC. I think that's my time.
Thank you. So that brings us to the end of this workshop. So thank you, everybody. Thank you, everybody who came and for attending. Hopefully, this was all useful. But again, if you have any questions about anything in this workshop or about anything kind of going forward, again, there's kind of, I think we have in some of the workshop materials, some of the points of context you can ask about MDAnalysis things, and then also if you have questions about the molecular node side of things, then you can reach out to the various Brady or Yuxuan about those. So just some final notes to wrap up. So this session has been recorded. So we'll eventually we'll tidy this up and eventually post this on our YouTube channel. So if you want to check back anything that you missed or share it with anyone who couldn't attend, then you can keep an eye out for that. We will send you a follow-up email with various links, including to the recording and also some of the things that I'm about to talk about next. One of which is, so we would love to hear if you've got any feedback from this workshop. We're still getting used to kind of running workshops in this kind of virtual format. So still, various things that might not, go as smoothly as they could, or, maybe things that went well, and would love to hear what you thought worked or didn't. So you could get started on that right now. Even it shouldn't take you long. There's a QR code down the bottom here. Also, having now played around with Blender, if you had, so as Brady mentioned earlier, if you have any cool renders that you would like to share with us, we would love to see those. And when we write a summary blog post, we could share some of those as well to show people what kind of cool stuff you've been making. So there's also a QR code here for a submission form if you would like to send us any renders that you've made. So again, we're hoping to keep running workshops. So similar to this, or also exploring other aspects of, say, MDAnalysis in the future. So you can keep up to date with us on our various MDAnalysis channels. So you could join the Discord, look at our blog, and we're also on LinkedIn. And then last thing, so as Yuxuan alluded to, MDAnalysis is going to be participating in Google Summer of Code this year. So again, if you're not familiar with Google Summer of Code, this is kind of a program where essentially Google will give you some money to help us out writing code for or for any open source project, but you could come work for us at MDAnalysis. So a lot of I did do Google Summer of Code several years ago. So did Yuxuan, and Lily did a similar program with Google Summer of Docs. So it's a good way to get more involved with, MDAnalysis, and it can be a good opportunity for if you think there's any particular feature that's lacking in MDAnalysis, you can then kind of join that and have a couple of months over the summer to add that, and we would greatly appreciate any help there. So I put a link to the exact blog post there. I think so it runs for this is specifically for the Northern Hemisphere summer, because sometimes people like to forget that the Southern Hemisphere exists. So that would run sort of around July, August. I think applications are open for the next, open in April. But yeah, so keep an eye up on that for if you're interested. So that's kind of the end of the housekeeping things there. I believe, but yeah, so if you have any final questions about the anything we covered in this workshop or in general, you can go ahead and ask those now. I believe we've still got some time left on before the end time of the workshop. But otherwise, again, feel free to leave now if you don't have any further questions. And again, thank you for showing up, and hope this workshop was useful for you.
As a point for people as well, the feedback form will be anonymous. The Blender render one, we'd love to put your name on it, but the feedback form is anonymous and they're not linked at all. So please do be honest with your feedback. I would love to improve. We do still have time if anyone has any questions about anything. We can unmute people if people want to ask questions the old audio way.
Yeah, please feel free. Any questions about anything like generally MDAnalysis related, doesn't have to be relevant to this workshop, or Blender related, I'm hoping. Yeah, in text or live, as Brady mentioned.
I actually have an MDAnalysis question. If you, it's not covered in the for the transformers, like with averages and stuff. Can you remove transformers once you've added them, or like update them?
I don't think so. I think if you add like a transformation, you cannot even add it again because it will just read an error. I don't know the reason for that.
Okay, so once you've added a transformer, then that's just the one that's on the trajectory forever.
Yeah, well, you can always reload it as a new object.
Yeah.
But yeah, I mean, the real answer is it's Python, so you can hack whatever you would like to hack. I'm sure there's just a headline list somewhere, but there's no endorsed way to do that.
Okay.
I'm guessing your computer is really great, Brady, because I was following along. I was trying to render, and maybe this was a bit too ambitious, a whole box with a bunch of solvent as well. And it just crashed about halfway through your tutorial.
Yeah, look, I mean, I did spend a lot of money on my, like, much more than my car is worth on my computer. But I also, my car's not worth very much. Yeah, like I have a 3090 graphics card, which was sort of top of the line for a while. And it's just because I use it so much, like I just put a lot of money into it for all this sort of thing. And yeah, it's inside of Blender, if you keep everything as those point clouds, like the spheres that are in cycles, I've had 500 million atoms on screen, and it renders them all, because rendering as point clouds is extremely memory and computationally efficient. And so it is like large scenes can get pretty large before it starts getting problematic. But once you start doing things that aren't just the perfect spheres, then crashes a lot earlier because you have to deal with all sorts of complex geometry.
And when you say render, do you mean actually full out render as an image with ray tracing and everything? Or do you just mean look at in the, I don't know,
Well,
the stage?
so like when you're looking in the 3D viewport, really, regardless of whether you're looking at it in like rendered view or like 3D view, like they're all rendering one way or another. They use different renderers and different approaches to, and I didn't even show, but Blender actually comes with a second renderer inside of it. And I do talk about it in the notes for the workshop called Eevee. And that's sort of similar to like a game engine where it's designed to be fast. And it's called a rasterized render engine. And so it can't handle the size of scenes that like Cycles can handle, which is the photorealistic rendering engine. It's much, much faster, but it's Cycles, because it does individual ray tracing, can handle much, much larger scenes. It's just much, much slower to render.
Yeah.
And yeah, I suppose when I say render, it's just sort of the actual ray tracing steps and computing what you're seeing.
Okay, cool. Thank you. Yeah, I wonder if it's a bit of a, it's firstly Apple, and which I don't know, it sounds like that should be a downside. It certainly is a fairly small laptop. So I don't think it was built to handle this kind of workflow yet.
Which is it, an M series?
Yeah.
Yeah, the M series does do pretty, like I have a M2 that I spend most of my time working from, and I just sort of use my PC for the actual rendering stage. And there is a like 1.5 engineers at Apple who are paid basically to just contribute code to Blender to improve rendering performance for Apple machines.
Nice.
So it is something that's improved a lot over the past like couple of years and is continuing to improve the performance on Apple machines. But yeah, it's not having the sort of, there's my laptop and there's my PC, which is like this big sort of thing. Like when you just don't have that kind of thermal capacity and ray tracing ability, then it does suffer a bit, but they still do pretty well. Sometimes you have to limit the sort of scene size that you're working with.
Yeah.
Well, this is entirely unrelated to any of the science, but if any of you are curious, this is my cat Pip. I hope you enjoyed his appearance. If you noticed that earlier.
I was going to ask their name. Yeah.
For the people who know their lipids in here, it's PIP short for like the lipid phosphatidylinositol phosphate. Which, I don't tell the vet that they would probably think I was insane. But the people here might know what I'm talking about.
The paperwork isn't the full name.
Yeah. If you have one of those tags with your number, I'm not sure that could fit.
Should we wrap it up then? Oh, no, another question.
But yeah, molecular nodes. What's the development pathway look like for you in the future? Do you reckon it's going to stay pretty stable, or are there going to be huge new features?
I'm basically developing it as fast as Blender develops, so molecular nodes uses a system inside of Blender called geometry nodes, which is the whole node graph based thing. And so that is only 3 or so years old. But Blender itself is moving towards basically everything happens via this node graph thing. Basically, so everything's reproducible, and you set up a node that says repeat. You're essentially just writing code that says do this 50 times. And the great thing about it is that the nodes themselves just call the underlying C++. So everything's really, really fast and really, really stable because, it's in a nice little box that you don't accidentally segfault stuff. And importantly, you don't have to write C++ because the devs wrote it for you. And so just by creating this little node graph, you write a C++ geometry processing algorithm. But because of that, you also need to wait until the devs have implemented the nodes that then you can use. So like for me, I initially it's like, all right, I could make the spheres, and then they eventually added the feature that meant I could make the ribbon, and then they eventually added the feature that meant I could make cartoon and surface, and so it's sort of as they release new stuff and it becomes more mature of a basically like a programming language almost, then I can add sort of more features there. And as like you could inside of Blender, you can execute any arbitrary Python code, and so you could do something in the nodes and call out to Python and do something and bring it back to get features that currently aren't implemented. But I've sort of held off from implementing that stuff because it's as if I keep everything as much as possible inside the nodes, then it's faster. It all works nicely together.
Yeah.
And it's also far less development time on my end because someone does the hard work and then I just, connect some noodles together and call it a day. But like in terms of development, it's mostly just going to be a bunch of UI improvements because they've done a lot of the sort of under the hood stuff, and they want to, over the next year, enable people to sort of build applications on top of Blender that sort of strip out all the stuff you don't need. So, the 500 buttons you're greeted with when you open it, you can strip out all of that and sort of get a dedicated experience that is more friendly UI wise. And so that's the sort of that's the sort of plan over the next year or so, is to sort of make the whole user experience a lot simpler as they add the features that are able to do that.
So how much effort do you need to make when Blender transition from 3.6 to 4? Like, do you need to change a lot of stuff inside molecular nodes, or it's just quite smooth transitions?
There was a bit of API breakage, which I had to sort of tweak to get it working, but it's not too bad. And like 4.1's coming out, and there's some breakage in there, so I need to do some tweaking, but they're pretty good with backwards and forwards compatibility. But yeah, that's the real sort of development goal, I think, over the next year or so as well, is going back the other way and turning it into a pip installable package that in a Jupyter notebook you can load a universe and render it from the command line rather than having to do anything. But then you have to develop an API that then interacts with nodes that then interacts with an API. So it's a few sort of layers of abstraction that it gets messy. But I think it's already promising, like what Yuxuan was showing off, importing into notebooks. And if someone does want to do a Google Summer of Code project on it, then I think we could probably get a lot done, because it's all sort of sitting there ready to go. It just needs someone to work on it. And this is, the only Python code I've ever written is just this add-on, basically. So I've just learnt through writing and rewriting it over and over again. I'd love some people working on it who actually know what they're doing. What is that llama?
Oh,
icon?
this is it's an alpaca.
Oh, my apologies.
A free particular free what do you call it, like drawing software.
Oh yeah, Blender's got a full 2D drawing engine inside it.
Oh yeah, maybe I'll have to switch over then.
Yeah, it's called Grease Pencil, and people are making like feature fit. Like, have you seen the most recent Into the Spider-Verse movie?
Yeah.
So a lot of the line work on all the characters was all done inside of Blender using Grease Pencil, because you can do 2D drawings inside like 3D space. So you might enjoy working with that, because you actually that's one thing can I share my screen really quickly?
Oh yeah.
So if I add grease pencil, that's Suzanne. They're sort of the mascot. Oop. Inside like 3D, you can just draw sort of any sort of shape. And so you can, inside of your like trajectory, use it like just like sketch on top of your trajectory. So you're like, oh, down to here. And now it's like, oh, here's this. Let me go. Go back into draw. Like you can do. Yeah, let me. Like you can sketch in sort of 3D on top of. If I cursor and there we go. And so you can go, okay, here's, you know, this part of the domain and it moves up here and then you draw on. Why is that not drawing now? Oh my God, what's breaking? It's something that I have sort of realized that you can sort of play around with. And so you could have like a trajectory that you just go in and you like sketch up and annotate in 3D rather than having to like go in and place labels, which is a pretty cool use case for it.
Yeah, that's real neat.
Yeah, it's something that I just sort of realized. It's like, well, of course you could do that, but I haven't gone through and sort of made it nice yet. But yeah, like because you can sort of just draw 2D in 3D, you can just sketch up your, like, oh, you know, look at this angle. Ooh, it's a bit big. This, you know, this one here is this far away from this one, or whatever. And you just go in and sort of annotate your structure, and then, you know, you can move through and then annotate somewhere else. That sort of thing. You can do it all.
Yeah, that's really cool.
Yeah.
Does it stay under the 3D object, or because it looked like it was staying with the structure when you were rotating?
Yeah, so it is its own 3D object. So basically it just draws curves with like a bunch of points in it, and all of these points are 3D space, but they just get rendered as like 2D.
Yeah.
And yeah, so you could even like you can draw some points and attach it to these atoms, and then as those atoms move, the label would like moves with them or whatever. And
That's really cool.
yeah.
Yeah, it looks like it's we're a minute over the allotted time period. Yeah, so I guess thanks everyone for coming. Hope you enjoyed the workshop. Please fill in the feedback form.